Okay, I think it's going. So, okay. So this is the day 2 of the digital future workshop of hierarchical modularity and growability space architecture. So today we continue what we left yesterday, and I'm gonna start with the review of assignments of participants. So yesterday we did the kind of basic agent algorithm reproduction based behavior. So I ask you guys to generate some kind of line work out of agent behavior. So I think I'm gonna ask each of you to show that by sharing screen. So first I'm gonna score the name. First, can show the assignment work?
Yes.
What? Can you share the screen?
Okay.
Yeah, I see the screen.
I create this visual to look like a ribbon. At first, I tried to make it look like a heart, like this, but I didn't work, so I made it look like a ribbon. I decide on the movement of the agent based on the image of the ribbon, spreading out, and used IG time to make the moment change and to be able to run random color.
All right.
I wanted to branch out from here and made the ribbon spread more, but I haven't do it yet, so I will try.
Yeah, to do that, you need to find like the timing, either just like a time equals 1,000 or something specific. So, but anyway, yeah, I think it looks good. Plus, I mean, it's even, but somehow it's in macro, it has some 90-degree turn somehow, which I don't know why, but yeah, I think that it's not just a simple rotation. It's like a ribbon thing or wave thing going straight and then turn certain angle. That's interesting. Yeah, I think that's good work. Thank you very much.
Thank you very much.
Okay, next.
Mr.
Yep.
Can I have a question about?
Yes,
about
go ahead.
Yeah, because I'm very at the beginning of the coding, and also I to my video, and I was studying the interact method example 1. And I was trying to understand how actually each statement are stand for. So I don't really understand the statements at the line 19 about when you declare the PT1 equals to PT, and the last variable, it is that does not compare in every else place in the code.
Can you share the screen and point out the line of the code?
Is this one.
Okay.
It's really simple, but I don't know how actually is working the line agent, and how passes from the point 1 to point 2 from the SQL to to another.
Right. So this agent, I mean, this is the line agent, which is a bit different from the agent we are working yesterday. And so yesterday we had the property of just position and the direction, but this line agent has the point 1 and point 2, which is like a starting point and end point. Then so that's the main difference. Although after that, but once so the line location is given by parent. So once it's given, it never changes. What this agent does is just to check if this is colliding into other agents or not. If it does, this disappears, and if it doesn't collide, it stays, and then it reproduces next line agent as a child agent. So yeah, so that's that line. I mean that line. So the point 1 is the start point. So when this agent doesn't collide, this agent is going to produce child agent. Then the child agent starting point gonna be point 2 of parent agent. So if you scroll,
absolutely. So this is the process that I didn't understand, that how come the line agent of the child is correspond to the 1 point of the
right. Yeah, can you scroll down to the update method? So you have 3 new line agent part, and then all of them have that first input is a point 2. That's the end point of child agent. No, end point of the parent agent. But that becomes the starting point of the child agent. Then the second part of the input is which follows is the direction of the child, and then so one of them is like a turning 1/3 of pi, like a 60 degree on the right, and then other 60 degree on the left, minus and then another straight. So yeah, that's how it kind of it maintains, or it kind of cascade the agents to the next, and then the next agent kind of stayed. So the parents get keep the point 1, and it gives the point 2 to the child, and that child start from point 2 of the parent, and that's the new starting point. So
okay, so can I understand that it's automatically updating that the starting point of the child agent corresponds to the end point of the parent agent?
Yeah, in a way, yes. The end point of the parent's agent corresponds to the starting point of a child agent.
Okay.
Yes.
And I have another question about the cast process that you have mentioned also in your website. And if you can explain what does mean, if the
casting,
if the line this class is already an extension of this superclass agent. So can I understand that this agent is already subclass of agent? So why we need this?
This is a purely Java computer language thing, which I mean some other language doesn't need this, but Java is okay. So this is Java language thing, and this is also very specific to the object-oriented programming thing. And then casting is that so in general in object-oriented programming, object you can make an object inheriting other object. Like you can have like fruit object, but the inherited the new class of like apple object. This is sharing the property with the fruit, but it's more specific. So in this case, a line agent is more specific than I agent.
Okay.
I agent has property like time, and then actually mostly time and some agent property, but the line agent has the property of 0.1 or 0.2.
Okay.
So this is more specific. So so in the when in interact method, the agent you are iterating through the input agent, like a interact parenthesis dynamics agent, that agent is generic agent. It says agent, it contains some agent, but you don't know what agent that is until you check with the if condition the agent instance of. But even when you know that, the container or actually the agent, dynamics agent is a still kind of abstract form. So this actually the actual thing inside is line agent, but the container doesn't look like line agent. And then so this part is this is the part which is specific to Java. Other languages doesn't care if it's the line agent or I agent. They can just try to pull out point one, and if it exists, it can take. If it doesn't exist, it can ignore or return something error. But in Java, because Java is a more strict language than other object-oriented language, and then you need to make it look like this is line agent, which is the operation of casting. Casting is it's exact same data, but just the appearance of the data become different. So so when appearance changes, the accessibility changes. Like now you know this has the 0.1 variable and the 0.2 variable. iAgent didn't have a 0.1 variable and 0.2 variable. So, but when you know that is the it's actually the line agent, it's inside the agent, then you can cast. You can try to the variable which is not a line agent, but in that case, it's gonna just cause error. So, but anyway, so this is a kind of a the analogy. It's appearance of variable, and then you need to change the appearance of variable to have access to the 0.1 and the 0.2 variable, which is a bit technical and the Java language specific thing, which is essentially not necessary, but yeah, this is true.
Okay, I see. Thank you very much for your explanation. That's explaining a lot of things. Thank you much.
No problem.
I still get familiar with this new programming language, so I need another time to show you something of.
Sure. Okay, then in that case, let me know when you get something, then I like to see that.
Okay, thank you very much.
Okay. Then I want to continue the assignment review. Okay. Then next, Aroni, can you show your work? I mean, assignment work?
Yes.
Right, go ahead.
So this is the basic code of what I did. I just took one of them and was playing with the numbers and the direction. And if I run it, I don't know if can you I don't think you can
actually no, you are sharing
Sorry.
not the output. Okay.
Yes, so it's basically it's more of like a fractal, I guess. Inside it just goes deep and deep and deep in layers. That's all.
It's a three-dimensional spiral.
Yes, inside it's just going more and more like more branching out inside.
All right.
I had a question. How do I increase the scale of it? Like here, I can see that it's kind of I can't zoom in as much as I would like to zoom in inside the spiral.
Okay.
How do I?
Can you focus by typing key F in the perspective view? That might change the increment of mouse. I'm not sure.
If I wanted to go,
but I mean, so kind of view now. Yeah.
Go deeper in, then how would I?
Oh, actually, that level not. I don't have better answer. than just it's a mouse operation thing. But actually that's tricky when you have like a whole thing is big and you also need to go small and very kind of small. Difficult. I mean, if you know where that's gonna happen beforehand, there's a way to specify like a camera location to be very specific location and a specific kind of zoom. So in that case, you could do so. Doing the interactively, I have like a general resolution with like a mouse navigation. So that's still kind of a bit tricky. But one thing about just initial, just the question that to make it bigger, you can change the initial direction of agent, like when inside the setup when you make the new my agent part.
Yes.
Then you have the second input which is ig.v100, right?
Yes.
The latter part towards the end. That 100, if you change the 1000, that's 10 times bigger.
This one here. Here.
That line, and then the second part, right, like a right side of that long line.
Mm-hmm.
The first part is IBEC 1000, right? But the second one after that is ig.v100. Not there, that towards it, right? Yeah, that one.
Yeah.
Yes.
Okay.
Okay. So that means that's the direction and also the size of agent as well. So currently it's the one line of agent is 1. If you make it 10, the one agent becomes 10. So, however, this doesn't solve the camera issue or mouse navigation issue, but to make it big, that's hard. So yeah.
Oh, wow. All right. And okay, that's good. Another question. I think the previous person he asked it, but I wasn't sure. Where is the starting point of each line? Like in the graph, I think it's
right. In this case, my agent has a property of position and direction, and the starting point is position. That variable. The first one actually in this case, the other one where you have the mouse cursor on the first part of this. Yes, that one. That. Okay. Yeah, so you have that 10 radius and the rotation, and then yeah. So I mean, the location is after rotated, but that's the starting point. Yes.
So if okay, so when we are branching out, say the first line gets extended, and then I want to branch out to another point, and we have branching points here, I think.
Yeah,
so where is like, how do I determine from which point should it branch out from? Like
that okay. For the quick question is that this code is not set up to do that, meaning you cannot do that. So because what you are thinking is like so each agent is each segment. It's not a continuous line. Continuous line is made out of hundreds of agents. Then they are individually different agents. If you want to identify this kind of strand or like a continuous line of agent, they don't know. They don't know where they belong to, which line belong to. So you have like 100 agents or 100 agents to start with, and you have 100 lines. But each of them have no idea which group they belong to. Then if you so this is kind of a design of agent, meaning current agent is a bit simple and a little bit dumb, so they have no idea which group they belong to. But if you want to let them know, if you want to have that kind of control, like this branch or this line gonna make branch, if this line doesn't gonna make branch, in that case you have to let them know where they belong, and that is a new information for them, like which group they are. Then so in that case your agent needs to have additional property of like a group number or who is the root parent or something. So that's a new information. And then actually, so then so like so you have 100 agents, so maybe group 1 and group 2 and then group 10 and group 35 or something. And if you keep that number, and then if you if the parent agent passes that information to child agent, so actually when you specify in the beginning, parents remember, but the child agent gonna forget unless parents tell the child that you are in this group. Then if you cascade this information to all of the agents, then now all of them know which group they belong. Then now you can specify the branching behavior inside the update method. So can you scroll down the code a little bit? A little bit more, actually maybe toward the end. Yeah, so the bottom part, like I round the %1 is the exact location of branching. So currently, randomly, any agent in any group can make a second branch in 1% probability. Currently, that's a kind of universal rule. But if you know the group number, if you give us the group number idea, and if you kind of know which one you want, like only group 20 can make branch, and or only like a 10 group 10 and 20 and 30 or something, you can write down in that update method, and then so you can add another if condition, like if group number equal 10. In that case, only group 10 line can branch, and all other cannot branch. So yeah, so that's how you would do if you want that kind of behavior, which requires this additional information. So in this case, the agent become a bit smarter with this new information, and they know where they belong to. So then you have the control. Is that good? Good. All right, thank you very much. You don't have any other question?
I have lots of questions now, but I'll wait for the workshop. Thank you.
All right. Okay, thank you. And then next, Giuseppe, can you show your assignment work?
Yeah. Hello.
Yeah, I hear you.
Okay. Please let me know if you can see the screen, because I always
I see. Yeah, I see the screen now.
Okay. Okay. So basically, what I try to do is try to recreate a sort of city landscape with using modifying the code that we did yesterday, and the idea is like to create like this sort of more random pattern with different lines, and also with some interactions in between. So I try to create the structure generate the growth. I have a couple of questions as well. First one is, I was trying to, actually I spent yesterday most of the day looking into the documentation, and I struggled a little bit to find, find things quickly. Like, for instance, I was looking for some methods for extrusion in this case, or like XY plane or things like that. It didn't work for me, actually, the search bar on top of the library. And also, when I was doing Control F, I was able to search only that particular text in the page that was open. So I was wondering if probably it's only my problem, or if there is a quickest way to find things inside the documentation. Because, for instance, like I was looking for a plane, but obviously plane it doesn't appear like immediately in the front page. It's probably nested into, for instance, I used the IG part documentation where I found pretty much everything I needed. I was wondering if.
Yeah, actually, reference or the educational resources not much like outside third party kind of shared content not available. So most of the stuff is on the web page, and then These for like when you want to like generate a bunch of different type of geometries, it's most that's actually major one is on the tutorial, but beyond that its own difference, meaning that that's all we have now. So what I think you use what you search is a kind of all we have now, and then then beyond like if you want to go deeper, there's a deeper part which is the source code on GitHub. GitHub has full open source code there, but it might be I mean that's very deep, kind of deep place to see. So yeah, searching searching like for example, if you are imagining like how you would be generate like a cube, and in that case you would search cube. Although actually I'm using the term box, so that part will be a bit mismatch. But searching on the tutorial side or the reference is a bit actually that's the kind of fastest way, and the fastest way to like just search a keyword and then find some method and class. Actually, that's kind of right way to do. And beyond that, sadly we don't have more information right now. So yeah, that's what it is now.
Okay, that's great. Thank you. Thank you. The second question I think is more probably processing related because I normally like use Visual Studio, so I'm not great expert actually for the interface. Was wondering if maybe you can show us some ways to control the camera, like I don't know.
Camera. Later, actually tomorrow or after that, we are because we need to produce some animation, so I'm gonna show you how to control cameras. So yeah, you can specify very specific location setup, or you can also make the animation if you want to. Most of the time I use kind of automatic focus to capture, but tomorrow I'm gonna show you how to move camera or kind of let the camera follow geometry and then also capture the images to produce animation. So yeah, you're gonna see some control there.
Okay, thank you.
All right, thank you very much. Okay, then I think we wrap up the assignment part and then we move on. Or actually, I'm gonna ask each of you to send me the processing code to my email. Actually, I think Aroni already sent me. So yeah, the other people, if you can send me, that's great. The record. So okay, then okay, let's move on to the topic of the day, which is the hierarchical algorithm. So let me share my screen. So today on the tutorial page of the IDEO website, I'm gonna go into this multi-agent algorithm, and to the bottom is the clock stack agent algorithm, which I was talking yesterday. So the thing we're gonna do today is basically get familiar with this algorithm, and because this is gonna be the base of our design project of kind of modular space architecture. So we're gonna use this algorithm to kind of accumulate and then aggregate a module in a hierarchical way. Actually, so there's a level of kind of hierarchy and then geometric behavior. So then, but yeah, to start, I need to see the code. But the way it works is that this is very specific type of algorithm. So this is still one kind of reproduction-based agent algorithm. So it's same with that one we had yesterday, and so they just keep copying the child agent to next to it or whatever direction. So, but beyond that, as I mentioned yesterday in the presentation, they change the behavior based on the timing. And then timing is coming not from like global time or internal clock, but the it comes from the hierarchy of clock. So every so there's a second there is like every second clock and every minute clock and every hour clock, the kind of stack of the layer. Then the whole code is actually is written here, which is a bit long, and then kind of I set up the system to focus on only the rule of behavior. So there's like the collision detection is already done automatically, and there's the internal clock I set up in a very specific way and how to manipulate that. That's all done automatically, but only the part I'm gonna ask you to change is this one method called rules. So yesterday we are playing mostly with the update method inside agent. So but this already kind of used to manage other part like changing the clock level and then moving forward or actually copying the new agent, how many which direction, and making geometry, that kind of thing is already taken care of by this other part of the code. And but you can change the behavior by changing this rule part. So today we just write or change this part, although this part is quite tricky. So but anyway, so to start, I'm gonna copy and paste this whole code first. Then I ask you to do the same thing. So I'm gonna copy the code and then I'm gonna start new processing. Maybe I can just use this and I went. Okay. So this code also has several different classes inside that, but that's not that too important thing. Actually, just one more. But then, well, let me just run this first. So this gonna make this circular, like a circle of circle behavior, and then so okay, first let me change the window size. I'm gonna make it bigger to see, and then I also just for the view, I'm gonna change the view of the kind of processing output window. Currently, it has 4 view, which is the default, but you can start from one of them. I mean, later for the animation capture purpose, you might want to stick to one specific camera or perspective, or action, or top view, or something. Then right now I want to limit or just start with the only top views, and this method, like id.top, makes it happen. So in this case, it start with just top, although the camera location is not right, so I need to type F to focus. But anyway, so this is the behavior of this agent right now, and the reason why is in blue, and then actually so several things. Actually, so those are the comment by the double slash, but there's several actually thing I need to explain, but the actual code is this last 2 line. So this is made out of 2 behavior, and actually which corresponds to like the one line corresponds to making circle, and another line corresponds to making circle of circle. And then so this one is about making circle in the first place. Then it says next and rotate, so and then pi and something. So yeah, you can kind of guess there's a rotation happening. So this rotation makes the circle, and then but there's another thing happening here, and then which is, I mean, first they have the if function, and then inside if function there's a method called clock, and then some number, and it says something next, and then something rotate, and some rotation, and then some number. So actually there is also some number here, but for those keywords, actually the method is the main thing you're gonna use today, or possibly rest of the workshop. Then so actually there's some description here. There's a clock method and some explanation and next and some other next. Then, so just to start with simpler condition, let me just comment this first line of the rule and then just show you this second one, and then show you what that does. So as kind of you can guess, it just make one circle, and then that's because it's making just one turn, and then that's all. And so then clearly second one is about making circle, but more specifically it's making branch to specific angle, which is this angle, negative half pi, which is 90 degree to the left. Well, actually, right. So actually, let me just go even simpler. So let me explain this method next. Next is the method to create child agent. That's all. So, but it takes two input. One is a transformation, and another is a clock to increment. So that's actually the second number is an important part as a concept in this hierarchical agent. This specifies the hierarchy, like a both. So this when you put 0 in here, it means the bottom clock is incremented. So like every second is changing with this number 0. But the one level higher kind of clock is level 1, and then one level higher is level 2, and level 3, and level 4, and you can have any number of kind of stack of clock. And then later you want to say that what that means, but so that's the meaning of this 0. But the first part is just a transformation. Rotation is, so we saw rotation, and we also saw the multiplication yesterday, so you can also scale down. Then you can also combine that. So this whole thing means create new agent with the direction changed with this transformation, and then change the clock number or clock level 0. So that's the meaning of that. So and then you can, as we did yesterday, you can multiply some number as well, and then in that case, use cascade the method after the other transformation method. So, for example, if I put like a rotation and the multiplication together, that should make spiral. So that's kind of same with yesterday. But what's different is the now you have control over clock and then the level of clock as well. So only with this one, this is exact same behavior as yesterday. But now when you use the clock property, so now you have access of clock. So this corresponds to the time, like ig.time or just time, which we are using yesterday. Now we don't use time, but instead we use clock to check the internal hierarchy of time. So in this case, this child agent is changing the bottom clock number 0. So when you say 0, that doesn't mean setting the clock time 0. This means that ticking the clock at the level 0. So if the current time or current clock second is like a 3, putting the number 0 means it become that make the number 4, like a one tick forward. So then if you change if you check the clock, then if we like 7 steps of the clock 0, if you want to do something else, in this case branching, in that case you can use that in this if condition, and if that number is 0, you put another behavior. The another behavior is making child agent, and in with rotation 90 degree. And then this one, the third one, actually, like a second part of this first rule, this now it's set changing the clock number 1, which is a 1 level higher clock. Then the very specific behavior in this algorithm is that when you tick the higher level of the clock, so this is analogy of like a second and the minute. If you change or if you increment the higher level clock, all the clock below resets. So when the bottom one is going through and some number like 0 to 1, 3, 4, 7, but if you change the upper level clock 0 to 1, the bottom one reset to 0. So when you click that, it resets whole behavior and it start again. The whole agent, actually not whole agent, but a newer set of agent gonna start again from this new location. And then kind of, I mean, it remembers the clock level 1 is now not 0 but 1, but so it starts the second round of same thing. So that's the hierarchical behavior part. You change the higher level and it reset the whole below, and it restart from there. So that's kind of that's end. Well, not, it doesn't end, but it kind of restart the behavior, and that creates a module of this circle thing. So, but anyway, that's the conceptual explanation of that, of use of clock, and then use of this next method, and then the meaning of the second number. So let me, for example, I changed the transformation with multiplication, so something changes, but let me run this code again. So then, but you can see that we doing, well, actually, one thing is that because I changed the transformation, then this transformation is affecting the starting point of the second circle again, so it doesn't, so it keep kind of getting smaller. Plus there's a certain collision distance, so at some point it kind of stop. Plus second one cannot really make the spiral because it just collide into the parent. So, but anyway, that's a result of adaptive behavior, which is difficult to predict. But anyway, the main point is that this hierarchy. Hierarchy of like a circle of circle came from this clock thing here. Actually, I want the line above. So this number and this number. So then, but for example, if I don't reset the clock, what's gonna happen is that I can branch once, but it stops because from here to here, the clock zero changes from 0, 1, 2, 3, 4, 5, 6, 7, and 7 branches, but I didn't reset the clock. I keep using the clock number 0, and from here it continues to from 7, 8, 9, 10, 11, and then both of them continue 7, 8, 9, 11, and so forth. So it doesn't restart. So it doesn't repeat what I instruct them to do. So in this case, it doesn't. So it's not like a module thing. It's one thing and ends. Of course, you can instruct to do like every 7 or like every time 7. The branch. Okay, that becomes similar to what we are doing yesterday with the modular operation, like with the percentage sign. So that was a bit, that repetition was something kind of related to this kind of behavior, but a little bit different. This one has a more than that. Like you can have a nested information much more when you use a higher level of clock. So, but anyway, so that was kind of demonstration and then explanation of those. And let me show even like a simpler version of that for your understanding. So the simplest form of this behavior is actually simplest is nothing. In that case, no agent gonna show up and no child agent is created. But the next simplest is like next 0. You can ignore the transformation operation if you want. In that case, the direction of agent stays same, so meaning it goes straight. And then, but you cannot omit or you cannot miss the clock number to increment. So simplest one is like next 0 means the next agent it maintains the same direction, and then only the bottom clock changes. So this is like the first example I showed yesterday in the my agent example, and then this is just a straight one, right? And then you can rotate the slide, and that becomes same with the above rotation and or whatever. Then now it rotates and something. But now you can you can have that second level. Second level is the use of the clock, using checking clock with if condition, and then do some other behavior. So for example, actually I'm gonna put it back to the just next 0. So here actually you can follow what I'm writing, or actually I'm gonna give you this code, plus you can watch this video later on YouTube as well. But anyway, yeah, try to follow if you can. Then so next one is I want to use the clock method to check what's happening or put another behavior. So what I want to do is like I want to go straight for some time and then turn some direction. So I use the if condition and the clock 0. So clock 0 is changing from 0 to something. So maybe if the clock 0 become 10, I want to turn. So I want to turn to. So I want to turn, but that means that I need to make a next child agent in 90-degree turn. So next and then rotation, and then 90 degrees pi divided by 2. The actual so. Then here is a one thing. So when I have like a higher level behavior, then I should change the clock at the higher level. So if I was using 0 before and then I want to use 1 now, then this resets the behavior. I mean, it is reset the behavior at level 0. So in this case, I want to go straight and turn and then maybe straight again. So I'm gonna use the if and else, and I'm gonna explain the difference of just if and else soon. But so this creates this square, right? So I have two lines. Wait, I have two lines in rule or two rules. But now so this the second part is just going straight, and then so this moment at the corner is this 90-degree turn here at the 10. So 10 of line continues here and the turn. Then the behavior resets there as well. So it's reset here, and then now it starts from 0 at the clock 0, and then keep straight for 10, and then now it goes again. Then but the internal clock of level at level 1, it actually keeps changing. Like it changes from clock 1 being 0, and the clock 1 being 1, and the clock 1 being 2, and the clock 1 being 3. So that one is actually changing. So you can use that to do something as well. So for example, if clock 1 equal 2, but one problem is that clock 1 is being 2 at all of here. So but let me show what I mean. So I'm gonna make next thing rotation. Maybe I'm gonna rotate to the other direction, negative pi and 2, and I'm gonna change the clock in yet another level. So level 2 clock is increment it, and then see what happens. So now you see, okay, something else, but I mean, intuitively you see the meaning of the modular, like a higher level or something. You start to see the different type of repetition. I mean, repetition of repetition of repetition. So that's what's happening. But anyway, the way exactly what happened exactly is like here. I said clock one being 2, and I think the first location it started from here on the central square, that right bottom corner of central square, and then that was the starting, and then now the top edge was the moment clock 1 being 2, so that's the party start kind of turning that way. And then I mean they stop because they kind of collide each other, so that's kind of the just kind of self collision. But then about actually one of them survived, like a last piece or last last turn. This one it could turn, didn't collide into some other, and it just kept going, and then but it kept going, and also it reset the whole clock underneath, like a level 1. So it's reset, so it start again the whole like whole turning, and a bunch of branch is reset from 0, and this starts from here, and then turning, then the whole bunch of branching. So then same thing happen here, and like 4 times. So I mean, I didn't set to have 4-time repetition. They just kept going and then collide into itself, and it stops that. So that's the result of that. But anyway, so but anyway, so that the point was this number, like a clock number 0 behavior here, and the clock number 1 behavior here, and the clock number 2 behavior here. So that's how kind of you accumulate the behavior. And then but anyway, so this one I just wanted to show the example what happened. I checked the clock number 1, but let me go back a little bit simpler version. But before that, let me save this code first. That this is Day2. And sketch. Okay, so then actually, so this second one was making the behavior a bit complex. So let me delete this and go back to simpler square. So okay, so this square, just square. So this is just a result of 2 level of going straight and then turn. Then so I wanted to explain the difference of if else or just if, and then I mean difference in terms of the behavior kind of influence. So let me just show you what that means. So with if and else, it's just either behavior that was making the square. But if I don't have else and then only if, the result is this thing. So they don't stop, meaning they turned, but they didn't stop. So at this moment, actually this moment on the right bottom corner, one of them kept going, and the other turned. And then the turning is the first part, the clock 0 being 10. It creates a new child on the left 90-degree turn. But the first level, actually the line below this line kept going because I didn't exclude, or actually I didn't choose either turn or go straight. I said sometimes turn and always straight. So that's the result of that. So that meaning if you don't have else, then the exclusive condition, it means branching. So when you have sometimes have two next happen at the same time, that's branching. I mean, 2 or 3 or any number of next statement that are gonna be creating branching. So in this case, it's it created this branching thing. Although not necessarily creating the modular behavior or hierarchical behavior, because I didn't instruct in that way. I just kept it going. So that's one behavior. So, but anyway, another thing we can do actually. So usually it's safer to maintain if and else, or if and else if and else if or something. So then only when you know you want to make branch, and then it's good to have both actually. Both actually the better control is that this one is square, right? But then if one else. But if you know you want to branch, you don't want to kind of close a square, you want to make some of them keep going. In that case, it's actually better to be organized to have this one here. I mean, this gonna make exact same behavior with the other one, like without else growth, and then but this one kind of look like making branch because you are making two child sometime, and then other time just one line. So it's kind of generally good to have if and else all the time. So not just if and then else sometimes. It's good to have else, and then it's in that sense it's also good to have like you have if you have many conditions, and in that case it's good to have the if and else if and else if and then else all inside this condition clause. So but anyway, so that was about the topic of if and else. Then let me just keep explaining a bit more stuff. And then, for example, but in this case, like, so this is like a bottom level, just the straight behavior. And then this is a 90-degree turn behavior plus branching. And then, but this second level behavior happens only here, but the level 0, the first level, still happening, which didn't create that kind of repetition of modules. So what if I change this number to be 2? So this is branching, this goes straight, but now internally it's a level 2 behavior, meaning it reset the whole thing inside, and then it try to keep going. So the difference gonna be like this. Actually that looks like grid, and it is grid, but to explain what happened, let me stop in the middle. So let me start this one, and then I stop too early. Oh, by the way, when you hit enter key inside the processing simulation window, it stops the agent, and then it pauses, and if you type enter again, it resumes the execution. But anyway, so this is a kind of snapshot in the mid at some point, and then so what happens is this new behavior is that so this one goes straight, and then this is a moment make the 90-degree turn and also branch. I mean the original one is just going left and then try to make a square. But the straight one now use the level 2 clock, meaning one hierarchy, and then reset whole behavior to the beginning. So it kind of start again from this behavior. So this one try to draw the square again, and also branch at this point. And then same thing happened here on the top right corner of the first square. And then the straight one is now, it's starting from like a y direction. But again, we set from here in this location in y direction, so it goes straight and try to make square here. Then, but again, this is another one starting from this corner, ending corner. So it keep going. So then, as a result, it's creating this grid, but this diamond way or kind of spiral way. So, but it's an accumulation of this like a geometry trying to make square and branch and square and branch and then it goes on. So, but anyway, so that difference is made by this clock specifying. So that level 0 does nothing. Well, it can try to stay the low level behavior, but the level 2 makes that try to reset the behavior. But level 1, I'm not sure if you put the level 1, it does make the level same with the second one, which might make same thing, kind of, or actually exactly same. The internal logic or internal information when you want to compare something, there's a difference, and but actually later it's gonna be different. So, so right now, if I want to make that square thing, and then it's okay to make keep this one. But if I want to use this information level 1, if I want to use a level 2 clock information, I need to give it 2. But right now, then let me actually, that was an example of changing this number simply. So okay, first let me save this one. And actually I wanna step backwards again to go one step simpler. Then the next thing I want to show is first of all, I don't want to branch, and let's make it simpler. And then just going back to square, but I want to use the clock level 1 for if condition. So and then clock 1, I could use the clock 1 if condition here, although I could also do that somewhere else. However, but anyway, for example, clock 1 something. So clock 1 currently means that number of edges, like first edge is clock 1 0, and second edge is clock 1 number 1, and the third edge clock 1 number 2, etc. So this specifies the location of edges or somehow. And then, so as I showed before, this was making clock number 2. Yeah, okay. So at the, let me repeat what I heard yesterday, like not yesterday, the moment before. When clock 1 is equal to, I reset the clock and then make branch. So this one, I mean, I paused the execution, but but this was branching because I didn't have else. So in this case, these 3 rules are exclusive, so they don't branch. But they don't branch means they don't branch means this shape. So now, I mean, so clock number clock 1 being 2, that's this moment. Before that, that was still like a branching moment in the clock 1 was not changed. And but anyway, so because it doesn't branch, that just one line continues. Also, you see certain shape repetition. Then, but this is like a fast. So this kind of small turn, actually short edge and the small turn. So this short edge is actually the moment when the clock 1 become 2 for the first time, or like so right before the clock 1 was 1. So, but what if you want to continue this line a little bit further, not just turning here, but maybe turning later, like turning in the middle or something. Like if the edge is 10, and maybe I want to have this turn 5 on the second edge. So if I want to do that, the control is gonna be like the clock one needs to be 2, but the middle part of the edge. So so the second edge, actually third one, third edge, like a first edge here and second edge here, and the third edge and the middle point. That two conditions I need to specify. And then the third edge part is specified by this clock one equal 2. And I need to specify the second condition and they put together. When you put multiple condition together, you connect with this sign to an ampersand sign, and that I mean in Java it's called AND, simply AND. So it's AND condition. So you want to say clock one being 2 and something else, and the something else is going to be the middle point. So middle point is in our term in this clock edge, and that's a clock number 0. Actually, clock number 0 means that from 0, 1, 2, 3, 4 to 10 or something. So clock 0 equal to 5 might mean somewhere middle. Actually, no, clock number 0 equal 5. So that's this. So now it kind of continues to kind of middle part and then turn there. So, but again, so this is example kind of about showing the multiple clock. So when you have that several level of clock, and if you want to specify one moment, and you need to have the multiple condition because you have 3 clock, in this case 3 clock, clock 0 and clock 1. Actually, no, it says 2 clock, clock 0 and clock 1. If you want to specify one moment, you need to specify 2 clock. And otherwise, you are specifying multiple location, and then many things happen. I mean, if that's what you want, that's great. But if not, you need to have this and condition of 2 clock or 3 clock or some more. So then if I want to kind of keep continuing or adding more levels, I could. Okay, let me stick to the example I have here, not this one, but so square and square thing. So let me go back. So this one kind of repeats what I was talking about at the same time, a little bit different. Let me talk about this. So in that case, I save this file. Then the next, then by the way, if you have a question about what I'm talking, and yeah, go ahead to ask me. Then okay, actually today, yesterday I wasn't having any breaks, then which I should have. So I gonna have break this today. I maybe in 40 minutes or something. Although I gonna give you the exercise time as well. But anyway, so
I had a question.
Yes, go ahead.
When we in this code we are making, for example, a rectangle. So where is the part where the rectangle is like ending? So you're giving the clock for the distance, like, and then the turn, but then where is the box ending? Like, what's the code for?
Okay, let me explain that part. So I have no instruction. Rule doesn't tell to end the rectangle. Actually, that's an instruction. Meaning, it ended as a result of collision. That's all. So it was colliding itself, and then it stopped. So the collision detection is automatically on in this algorithm. So when they kind of collide into what's existing, they stop. Which means like if this code. So for example, if I so So this one is, this one is not rectangle, but weird shape. But if I don't have exact 90 degree, it doesn't necessarily make that kind of orthogonal shape. Plus doesn't collide back to the actually collide in some location. But for example, so the actually I didn't need to make the term, but so if I scale up, that never collide back into the original location, so it never ends. So the actual instruction was keep going. That's all. So it's supposed to go infinite, but it stops only when it collide. If you want to specify, that's actually you can do that by actually let me change back to, first of all, let me save this and then let me make simple rectangle first or square. So if you simpler one requires only the clock level 0. So then, so if you want to specify the end by rule, so that's the time you put you use the clock number. Like currently, so edge 1, the first edge is having the clock 0, actually no, clock 1 being 0, and then this one is a clock 1 being 1, and being 2, and then 3. So when it time to 4, it should not continue. So meaning if I have a clock number 1 become 4, it should stop. So when it should stop, and then I have this else. When it should stop, you say nothing. Meaning if you don't create child agent, that means it stops there. And then so this gonna stop. However, one thing is it's actually it gonna collide before it stops, so it doesn't really what I'm trying to show. So I'm gonna make a spiral to have the example of that. The one more thing is that it has one final thing. So when it so that that's one way to stop. However, maybe you didn't envision that this one final thing, because this one line on the toward the right is still the previous child. This is the last child of clock 1 being 3, and then clock 0 10. So this guy. So if you want to eliminate that, actually you need to stop at the end of clock 3. But anyway, so you can specify the end in this way, like being clock number something and number something. You do nothing. If you write down specifically in this way, or in this way, then you can specify stop. But what we are showing so far was having no ending condition, and then everything is supposed to go forever, but they collide each other and then stop. So that's a kind of natural result. Then so that's the kind of general direction we are going. So is that good?
Yes, thank you.
Right. Good. So okay, then okay. So let me do this one, rule 1. So rule 1. So let me, okay, I'm gonna save this one as well as another file, as a record, or something I'm gonna send you later. Then okay, let me copy and paste this rule. So from here, well, I can just maybe here. I'm gonna copy and paste. Replace this one. So this one, actually, first let me just run the code and then see the result first, and then let me explain. So this is a square of a square, like a sequence of square, right? Then we saw this thing like is having 0, and the first one is like turning. Actually, this one is turning at 9. So but the difference, actually, new thing is here. Clock 2 is inserted here. So as I mentioned, this one doesn't have the if and else, and this one is just if. So some occasion, like when clock 1 being 0, so which means like clock 1 being 0, so the first one, so like a first edge, and then but the clock 0 equal 9 means that the last moment before turn, or actually at the exact moment of turning, and if it's the first edge, and then it branches to go straight. In this case, there's no rotation, so it goes straight, and so that's the branching. So if I don't have this part, it's just single square. And if I have this one, it branches to straight direction. But this condition, like clock 1 equals 0, so that's the end of first edge. And if you change this number, like clock 1 being 1, that's the end of the second edge. So that would result in this behavior. So now it doesn't branch in this location, but it branches this location. And then, yeah, keep going. Well, actually, no, it just goes 4 times. Yep.
So yeah, I have a question. The number of clocks is dictated by, like in this case, the vector length that we set at the beginning.
Yes.
Of the clock. So
individual, yes.
So in this case, it's set by like what we see in the setup function, like IBEC 1000.
Mm-hmm. Yes, yes, that it's still applicable to that. Also, each edge of these squares are made out of 9 or actually 10 or lines. So when you change the so this one, still the length or size of the agent. Actually, this one is a line agent, so that length of line is specified by this. And also this will specify the direction, starting direction as well. So if you don't have 10, 0, 0, then instead if you start with 10 or 0, 10, 0, that start with the vertical direction. And also in this case kind of goes around, so similar. But if you say like a 10, 10, 0, that's the diagonal.
So in this case, for instance, if you specify with clock 12, it starts from.
Yeah, so if you actually want to like change the length, not as a whole thing, but like a behavior thing, yes, this is the location to change. Like this is 9 segment square, but if you have like if you put 12, that's a 12 step rectangle, one square. And actually, just to visualize easier, I'm gonna show each segment. So right now, actually, this part I'm not supposed you're gonna change, but as an example, just demonstration, let me show. I can create point as a point object, and then this one make it line out of position 1 to position 2. That's the beginning and end. If I put this I point thing, you see each location of agent. So that's what's exactly happening. That's point or actual location of each agent. And so currently that's is that 12 or 11? One of them. So but yeah, that's what's happening inside. So that's kind of easier to understand.
Okay.
Right. Yeah. So then okay, then let me put it back to simpler x direction start. So 10, 0, 0. Oh, by the way, everything is maintained in a kind of local coordinate. Like, so each agent has its own XYZ coordinate. So which means even when you start like a 3D or whatever direction, that maintain its own plane. So it can go any direction. Plus later I'm gonna show you like a 3-dimensional rotation, and then each case they remember which is up and then front and right for each of them. So So the order movement gonna be like this kind of orthogonal thing. So, but anyway, that was something I'm gonna talk about later soon today. So then going back to simpler one. So okay, I'm gonna keep this point thing. But then in case not to forget, I'm gonna save that new file. Then so I was talking about the meaning or changing this number. So it was originally the sequence, the horizontal sequence of squares, but now it's like 90-degree rotation squares, and then because I specified to branch at the end of clock 1, which is the second edge or vertical edge. If I instruct to a branch in the next edge, like clock 1 being 2, so this is a top edge, end of top edge branching. So in that case, what's going to happen is actually it collide back faster. So it branches out, but it's already come back to the or collide back to the first location. So that's what happens. And but anyway, so that and okay, in the similar way, clock 1 being 3, that's the last of the fourth edge, end of fourth edge branching. But problem is the end of fourth branching, before reaching the end point of fourth edge, it collides. So the last one didn't happen. Then yeah, it didn't. So actually that's collision is I mean, useful thing not to have too much chaos, but at the same time, sometimes I expected to happen because then like if you specify some behavior, but it doesn't happen because it collided and then that agent wasn't born at that location. So but anyway, the point is this: the control of timing and location by the clock. So the clock level 1 means something, and clock level 2 means something, and then but anyway, okay, let me make it back to 1, and then no, actually I already saved. So let me move on to next example. So now next example adds another level. I mean hierarchy. So first let me copy and paste. So here, the result is a square of sequence of square. So like a 4 square make one edge, one bigger edge, and then the turn here, and then turn 3 times, and then go back, or actually collide back. So what happens is in the code, actually, first of all, I just noticed maybe it would be easier to see the code if I have bigger font size, although too big, wanna make it too, well, okay, all right, so, okay, so now, now we have like clock 3 introduced, and then clock 2 was there before. Actually, yeah, clock 2 was there before, but one more behavior happening there. So, and then let me break this code down. So there is a if condition of, there is if and else of this one to this one. So this one is like next 0 means going straight at the clock level 0, which is the kind of lowest level straight behavior. And then, but so this is like a turning moment, and then clock 9 or clock 0 being 9, so that's a first kind of turn of square. But after that, there's some more thing happening. So if and else also nested here, actually, no, this one is if and not else. So there's just that, and which is same with last time. So last time we only had this. and this was the sequence of square. But now it as this part, something with the clock 2 being 3. So meaning of this one was an end of straight edge. End of straight edge, and then first end of straight edge, and then first moment, actually first edge, actually end of first edge. End of first edge is the meaning of this two condition. So, and then there's another condition, and also, so now clock 2 is the which was used here, and which was also using in the previous one. This sequence of square. The clock 2 also had a geometrical meaning. The clock 2 was actually the which square, like a first square, second square, third square, fourth square. So when you check clock 2, that specifies like either first square moment, or second square moment, or third square moment. When you say clock 2 equals 3, that's a third, actually fourth square. When you count in this kind of a computation thing where world, usually it starts from 0, so first is 0, and then fourth is 3. But anyway, but that's not that important now. But so third or fourth square is what is specifying. So it kind of read backwards. So third square, actually, okay, fourth square, and then first edge, and then end of edge. So third square, first edge, end point, which means actually third square, actually fourth square, 1, 2, 3, 4, fourth square, first edge, bottom edge, and the end point. So that's the moment new behavior happens. So actually that's the condition which specifies that exact location is specified by this 3 if condition. So then what happened is this one, rotation to negative 90 degree, and also the another level of clock is incremented, and then reset whole behavior, then start again. So that's why it turned here. So for example, so again, this one specified which square to turn, or that moment to turn. So like if I change it to 5, I should change to the different number of square in the one edge. So now it's kind of longer square, so it's like a 6 of them, and well, yeah, 5 means 6 square, and then yeah, 1 means 2, and then but anyway, so that's the meaning of those number or if condition. So 3 things. So right now, these 3 things are happening here, but also these 2 things is specifying the condition for this one and for this one as well. So but this is additional condition to turn, and then specify this number 3. So then yeah, so that's this is another level, like a level 3 introduced example. So yeah, clock level 1, 2, 0 and 1, 2 and 2 was checked, and so edge, and then square, and sequence of square. So that's 3 things. And let me save and move on to next example. So, but in this way, I just keep going, like keep adding a hierarchy of hierarchy, and then, but this is kind of whole point of this workshop, like thinking about the hierarchy of module. And then again, they still maintain the adaptability, which is actually mostly about the collision detection. So when they collide each other, they kind of stop in the middle of a building module, and so they don't really change the shape, because this is still maintaining exact kind of modular concept, but they can stop building module. But so they can have, if you are making module of module, you can have half module of module out of module. So that kind of thing is something we are pursuing in later. But anyway, so right now we are focusing on just building, understanding the hierarchy. So the multiple hierarchy. So it's kind of endless. You can put any number of stack of clock. You can you could have 10 clock and then 20 clock, but that's kind of correspond to a bit like dimension. So if you have 20 clock, it's kind of 20 dimension control, which is super tricky to do. But anyway, you can introduce as many hierarchy as you want. Then, so right now we have 3. So now we have 4, I guess. So next one, okay, let me copy and paste this next example. And I'm planning to have break and also exercise in like 20 minutes. So yeah, we're gonna have break at the moment, plus some exercise like yesterday. Then, okay, let me copy and paste here. And then first, so this is fourth hierarchy, and the behavior is that, so square of, so sequence of square of sequence of square. So that's 4 things. So wait, what? Sequence of square of sequence of square. Yeah, 4 things. So wait, actually no, this is 3. This is okay. So this is sequence square. This is sequence square. Sequence of squares. And this is sequence of squares. Okay. So what happened is that, I mean, we can kind of, I mean, imagine that just 4 things. So it kept doing the same thing as before, but it branches out at another location. So another location, something maybe related to another clock. So previously we are manipulating at the clock 2, but maybe now it should be using clock 3 to change the moment. So that's actually true, which is here. Clock 3 equal 1. So this part, the beginning is the same, like a clock 0 and 1 and 2. That's still the specifies the moment of here. That's the end of first edge of the fourth square. And then there's another if here. So then that is the location creating another branch. So, but this one is this one did not add if conditions like if clock 3 equals something. And then you could have this condition, and which would generate a little bit different result. But the reason why is that, so this 3 condition specifies this corner or this corner. I mean, it's repeated. But if you want to create another sequence of square, if you start from here, you're gonna collide in any direction. So already 4 direction is kind of occupied. Although actually you could have gone this way, however, that might be something else. So actual branching point is this location. That branching, okay, so this square was sequence of square wanted to happen like a side by side, and then actually no, I want it to be side by side and then repeat it in this way. So I needed to start from here. The new starting point is not here, like this corner of the first kind of group of square, but the right edge corner of one of small square. So I needed to specify this moment to have this sequence. So to think about this moment, so what's the clock of this moment? That's a thing I use to think about. So this one is a small square. So the small square is this one. And then clearly this is the end of this edge. So the end of this edge means clock 0 equals 9. Fine. But this is what in sequence of small square, what number of square this is. So from on this edge, like from top to bottom edge, and then this is like a first square of that And so this is first one, second one, third one, fourth one, which correspond to clock 1. So one level up. Clock 1 being 0 or actually not that. Clock 9 is, well, clock 0 is 9, that's the end. And the clock 1, actually, clock 1 means the edge of the, like, the first edge of square, and the second edge of square, third edge of square. Then the clock 2 means the first square, second square, third square. So clock 2 is the first square, which means 0. Clock 2 is first square. Actually, so kind of explain not from the beginning, but so condition there is condition of this location is clock 0 equal 9, like this one, and then so it's inside here. And the clock 2 is 0, the first square on the edge. But the edge number is like a edge number 0, or the first edge is this top to bottom vertical line. And the second edge is the left to right edge. And then the third one is the bottom to top. So this first edge, second edge, third edge corresponds to clock 1 number. Then clock 1 number needs to be 2 to be third one, like, because the first one 0, second one is 1, and the third one is 2. So end of clock number 1 being 2. So that this condition specified this specific edge, and then this specified clock number 2 make first square in this sequence. Then also clock 3 equal 1. Clock 3 equal 1 means that which sequence of square, like this 4 square is all clock 3 0, and this 3 actually this 4 square vertical is clock 3 being 1, and then whole right to left 4 square is a clock 3 being 2. So this specifies that. So but anyway, so that's the meaning of this. Actually, I needed this 3 thing, actually plus being inside the clock 9, clock 0 equal 9. That 4 thing, like clock 0 9, and clock 1 2, and clock 2 0, and clock 3 1 is the moment of this right top corner of a square of a sequence of square. That's how you specify. Actually, you really think about that. Actually, first, if you visualize what you want, and then to locate the moment, that's how. However, when you design, you don't need to do. You just try many things and then see what happens, and then pick the best choice you have. So, but just to demonstrate the each meaning, what if I change those numbers? What if clock number 2 equals 0, not 0, maybe 1? What happens there? So this makes the branching location different. Like, actually, no, something else happened, meaning that's not working. Clock number 2 means the first one, second one, third one. So I believe that's colliding something. So this one, actually, let me just keep changing some number randomly. That's kind of I also do frequently to see what happened. I kind of think this, yeah, collide itself when nothing happened. And that also happens as well. So I change the clock number 3 equals to, I guess this does something. Okay, so in this case, each branch is at the bottom right corner. Although it's kind of similar to the previous example, it kind of collides back to itself. So, so in this case, changing this number, some of them nothing happened because at the moment it tried to go that direction, it collides with other and stop. But only this one have changes. But for example, even changing to 3, I think this also have the issue, not issue, but the kind of issue of colliding back to itself. Like it now branches from here, so it only 2 of them kind of emerge and then collide each other. I even make it 0. 0 means the first group of a sequence. So in my branch to actually no, first moment it goes there, and they create this 4 things. So but anyway, so that's an example of first how to think or relate this clock to the actual location, and also introduction of fourth clock. So that's what happened. I mean, it's get kind of trickier, but at the same time, this is a bit powerful. Meaning like sometimes if you change some like, so right now, if clock is a kind of strict thing. So if you mess up, you kind of correct itself easily and nothing happens. But like changing angle or length, those things is super easy to do. Then when you have this kind of thing, you have a kind of full control, not full control, but you can easily start to see the unexpected repetition, like unexpected aggregation, but still maintain certain rationality. So actually, rationality is also something we are pursuing here. First of all, modular thing is kind of rational. Second of all, rationality like a module of module. Of course, we are thinking about cost efficiency not in realistic engineering sense, but in geometry level, which would benefit later in kind of actual engineering sense in the future potentially. But we are still pursuing also complexity, but starting with rational modularity, but hierarchical. So different type of complexity and different type of efficiency or rationality, but that's kind of the area we are pursuing. So, but anyway, so this kind of exemplify that level. So that strict control part is a hierarchical modularity and the rationality part. But at the same time, when you start playing with numbers, you start to get certain, different type of complexity, but still maintaining the certain rationality by the other part of the kind of modular behavior. So, so right now I'm going through the rational part, the strict part, so it's a bit difficult part. But later when you play with it, you start to see the many different type of complexity. Yeah, which one different. So, and then start thinking about the exercise, but let me maybe go one more. Plus, first let me go one more, and the second, then I'm gonna let you play with it to mess up and then try to generate something interesting. So to do that, actually, so this one to this one is kind of good example. So, first, and first let me save this code. Then second, let me copy and paste this code. So actually, this is another just level. So like we have 4 clocks. What? Yeah, clock 0, 1, 2, 3, 3, and then next I eat this as one more. So the code become a little bit more complex, and then like this, and then but clearly this is just again square of square of sequence of square of sequence of square something. So five things. So but it's kind of keep going and then making a grid. So this one doesn't collide back to itself completely. So some of them kind of survive, or not survive, but didn't come back to the location. Some of them can keep going and then keep growing. So in a kind of diamond shaped way. So that's an example. But what happened, or what made possible was actually, I should stop in the earlier moment when it was making bigger branch. So okay, so so now this sequence of group of square, big square sequence, it branches upwards and then rightward. Actually, the right is not stop, it just keep going, and then bottom. So the top and the bottom is new branch, so it's kind of 3 branches thing, but branch didn't happen at the exact same moment. So like one point it branch upwards, and actually I try to capture the moment in the simulation. Let me see. Oh, that one. Oh, okay. So this is a moment. This is like the 4th one or end of 3rd one. It I think this is, yeah, 4th one. 4th square first. So this sequence of big square is starting from this corner. Well, like a starting point of the whole thing is this left point, and then starting point of by the way, you guys see the mouse pointer, right? I assume, or I hope. So this is like a starting. Actually, no, this is the starting point of like a third square, and then this is the starting point of fourth square, and the fourth square and the first small square runs, but the third end of third edges, and it branch out or to upwards, 190-degree right. So that must be written somewhere. So like clock 4 is 3. So clock 4 should mean the big square number. Like first square is a clock 4 0, and then second square is a clock 4 1, and clock 4 2, and then 3 is this thing. And then at this moment, actually, so this moment many things happens. Actually, not too many things, but actually no, it's has the 3 conditions. So that's actually that corresponds to the 3-way branching, although it happens in different moment, but the rule is here. And then so everything happens in this fourth big square, and then so this one specifies this corner to go up, and then this one specifies where this should specify this corner something. So one of them specifies here, which is actually same thing with last time, but the another should be here at the bottom. So clock, instead of clock 4, the clock 3 will be different. Clock 3 is like a top edge. Clock 3 0 is top edge, and clock 3 1 is the right vertical edge, and then clock 3 2 is bottom edge. So that's a 3 thing. So but anyway, so that's fifth clock, like a 0 1 2 3 4 fifth clock control to enable this grid of sequence of square. So that. Then, but from here, now I kind of wrap up the strict part, like a difficult part to be control. But from here, like I gonna introduce like a more way to play with it. So for example, from here to next one, this is just changing the angle. So we could like when you have some like template code, or you can use this as template code to play with. But there's many number you can change. I mean, but clock number, this level is when you play with this, there is a huge influence, so that either go to total chaos or nothing happen. Like you can make it easily to have the code to show nothing easily, and then. But so the clock level number is the kind of biggest impact, and the clock number, like increment number, that exact number, not level, but just time is medium influence, and then the transformation is like a minimum influence. Like they don't really change the structure of a module. They only change the kind of local geometry. I mean, some of them have a huge impact, like. Some of them have a huge impact. Like so, right now you are telling every square to have strategy. I mean, these bottom level lines. If you then so this is a location you are instructing them to go straight. You are giving no transformation, so it's straight. But if you say some rotation, actually it has a geometrically huge influence, but I'm gonna put some actually I'm gonna just want to put whatever number, like 0.1. So if I just rotate a little bit, although 0.1 is not too small number to put. So in this case, you see that now it's not square at all, and then yeah, actually now it's very difficult to describe what it is, but influence is there. Then the plus you think the grid is totally destroyed, which is destroyed, but what they are trying to build is same. And then I mean, if you look into the analysis, you see where they try to make branch to make the grid, but they fail because it collided by into itself, etc. So, like if I make like a very small turn, you're gonna still see the attempt to make grid. So I mean, you see that they still try to make a kind of grid. You see this like a three-way branching here, right? But somehow when you come back here, it's totally different thing. And yeah, so that's the so this is a thing I start like suggest you to previous. So changing angle is one thing. Actually, changing angle in there's many locations to change. Like there's one angle here, or one transformation you can change. There's another one here, another one here, another one here. Well, actually 6 or 5. But they are in different level. So if you maintain the lower level, like lowest level, if you mess up bottom level, it has a bigger geometric impact. I mean, topologically same, but geometric impact is huge. But if you mess up or change like higher level, so this actually this one is not that interesting. So if I mess up higher level, so this is like a top level big branches. So if I change that is so they don't kind of start not matching up. Not even regular. I didn't put a regular angle, so it doesn't come back at regular geometry. But you see they maintain the straight relationship. I mean, straight sequence of squares still there. They try that, but you can see the angle is messed up, and then, for example, what if I put like the number and then, but so this is one thing I suggest you to play with. Like angle is one thing, and if you kind of get some understanding or grasp of like clock control, and then not at too high up level, but if you kind of see where that location is, and if you try to slide a little bit more, not here, but what happens if you have this at this location, and then for example, clock number 2. What if you change some number like here, and then that would change the location to branch or collide itself and nothing happen. Actually, no, this one is nothing happen. So in this case, I kind of killed this branching, and then actually it's always killed, so not that. First of all, not that interesting. However, this kind of change like a T shape to a branch, and then that would have very different result. So, but anyway, so including the failure, you can start playing with it. So this is a highest level branching, like a turning angle, and then like this is, I think this would be like middle level, which I'm not sure what's gonna happen if I multiply some number. Middle level means where? Oh, here. Okay. So that like a second square is not square anymore. Somehow it's kind of more like a pentagon, but yeah, so it messes up many things. So I mean, still like this edge is straight, and then you can combine with not straight edge as well. So there's another thing you can play with. But anyway, so changing angle is one thing, super easy to do, although the result will be very different. And then changing clock is a very difficult to control, but if you manage that, that's great. And then I want to show one more thing you could do. Randomness. Randomness is the interesting. And then, oh, by the way, so I messed up the smallest square to be not square, and then yeah, no, very far from grid system. So then I think they gonna collide itself and stop. So randomness. Randomness is something you can use. You can use either for clock number, which is actually difficult to use. So the easiest thing to use randomness is that rotation angle. So if I gonna say bottom level, so it's gonna be gonna have a big impact. But I run there's a processing random number generator, and also there's a IGO random number generator, which is what I'm showing. So iRand.get shows something like you can put two number and then you're gonna generate random number between two numbers. So like minus 0.1 to positive 0.1 and see what will happen. So okay, very not square. Maybe that might be too much. So, but it was a kind of failure case. What if I don't have a minus point? Actually, no, this is 1.0 destructive. So 0.1 to 0.1. Also, that shape was kind of interesting if we can make it. Anyway, yeah, so something else. Bit Frankie vibe, but so yeah, so those kinds of things is something you can play with. So you can put this kind of random number here, or random number there, random number there. Putting random number here will be a bit out of control, possibly. You can try, but I don't think that's gonna totally mess up stuff. Like not anything happen. So, but anyway, so I'm gonna ask you to play with this and also take some break at the same time. So like, we can have like a 10 minutes break / exercise, and then we can come back, and then you can show the work you do. Is that good? I guess. Right. So let's say take 10, right? Yeah, in whatever time zone. So yeah. Okay, let's do that, and then let's come back to see your exercise work, right? Then meantime, I'm gonna keep coding and also take break. So. Okay, let's wrap up soon and then go through each participant work. Okay, so wait, let me stop my. Okay, first let me stop sharing. Okay, so you guys ready to show stuff? Actually, yeah. Ina, can you show your exercise? Let me stop sharing and then.
Yes.
And then also, do you have the assignment work you did during the beginning?
I have the assignment from yesterday, but oh.
I just like to see that we did a review.
Yes. Just a second.
Sure. It's early morning there, right?
Very early.
Yeah, I know.
So this is from yesterday. The branch.
Mm-hmm.
I'm not sure if it's going. Oh yes. And another one to try.
Right.
And then from today.
That's good.
I was trying to do a. Not sure if I can. Yeah, let me just share my screen. And today I was trying to do a bit of a triangle type of thing, but eventually I end up in a infinite loop sort of thing.
Right. That's all right. Yeah, it's well, it's kind of try and error thing, and then I mean, in general, computation is try and error thing, but this one is just a tricky one. So the tricky part is that sometimes they can just quit each other and then not much happens. So, but usually that's. But usually that when that happens, you just need to keep playing with. Then you could like investigate the code to find out the exact moment when they are colliding. However, that's a very time consuming thing, and then not good thing for when you are not familiar with this code. So yeah, I just suggest that you just keep playing. Then that something happens, and then you take it, and then when you start to fine tune it, then you can look into the code and what exactly happened. You like a micro adjustment is something you would like in like finding exact moment and change slight angle or change moment or like a timing, etc. So that level, that's a good thing to look into the code. But in the beginning, just keep playing. All right, good work. Okay, then next, Jerun, can you show us the exercise work you just did? Or if you are back from the break, or Jerun, okay, not responding. In that case, I move on to next person, Shoko. Can you show us the exercise work?
Yes. Oh. Sorry, wait. Okay.
All right. something happened?
Yes. I have Java error.
Okay. Was it working before and then now not working? If it was working and then not working now, possibly.
Before 5 minutes, this code was working, but
Okay. Yeah.
So
I mean, if it's if it's related to somehow to the this. Okay.
Working now.
Yeah. Good.
All
right. Oh, you change that color.
So
cool.
I wanted to try to use island. So I made a geometry with curved shape that's spread out and random color.
Right.
That's all.
Good. Yeah. Yeah. Very random-ish. Okay. All right. Interesting. Good. Thank you very much.
Thank you very much.
Right. Next, Giuseppe, do you have a exercise work you can show?
Yeah. Nothing major actually, but I was trying to go through the definition. So what I did is was working on the example with the hexagon and trying to change it in the location of that and also the size to create some random patterns. So basically, with a different length also between the elements. Different distance, and then it creates this sort of pattern that grows and concentrates. Yeah.
All right. Yeah, it's very hexagon, but yeah, I mean, looks interesting. I mean, plus it has a, I mean, if you look close in terms of movement, you notice that like the direction is kind of alternating, like the way hexagon is work shape pentagon now is created in like one direction the clockwise, another direction anti-clockwise. So that was there's some operation there, like instructions there to flip the rotation direction. But anyway, but yeah, good attempt. Great. All right.
So
thank you.
The flip. This is one other question actually. The flip method that there is in that in this example is basically it just inverts the rotation, like the.
Yeah, the thing is that I think the exact example is using the operation to flip normal direction or something, and then they actually, as I mentioned before, that this each agent maintains the coordinate system inside. So each of them knows like which is front for them and which is the side for them and which is top for them. Then that's all relative. So each of them have a different, or each of them could have a different coordinate system inside. But when you flip the normal, which means it's flipping the whole coordinate system. Actually, it's not even rotating. It's actually there's a world of the left hand coordinate world, and there's a world of right hand coordinate world. So it changes. So when it changes, if the normal, actually, it normally actually goes up to down, but at the same time, like the side stays same, so it goes to the other world. So the right road, like in the regular coordinate system, positive number rotation means counterclockwise rotation, but in the flipped world, the opposite world, the positive number rotation means clockwise. I mean the other opposite direction. So that's why even when you are rotating exact same way, when you flip the whole coordinate system, the rotation changes the other way. So that's why it's changing, alternating like one another. So that's why.
Okay. Yeah. Thanks.
Yeah, but in so that's a kind of mathematical kind of operation happening behind. But when you think about the flipping to the modular architecture world, like one module and the mirrored module, that's not. It looks rational, though it's not rational because you need to produce two different modules. So flipped world usually doesn't really work for the construction rationality. So yeah, something. But also, if you rotate like a 90-degree in the space, then that works. I mean, that's the same module. Also, the flip normal operation in the code is actually mirroring the whole world, so it creates a different mirrored object if you want to put something. But there's another operation inside the code which I'm gonna talk at some point, either or possibly today. There's a way to rotate 90-degree along front axis. So in that case, it just rotates 90-degree in the upside down. Actually, upside down module might or might not work, but in that case, it's geometry is same, but rotated. Then the behavior different. Still rotating the other way, but it's upside down. Something else. But anyway, so yeah, it's the kind of version. Then yeah, I'm gonna talk more about that today later. So all right, thank you.
Yeah, thanks.
Okay, so Aroni, can you show your exercise work?
Yes.
Yeah, go ahead.
I just did like an inverted. What I was trying to do while working in the code was I wanted to expand it outside, but it was only internalizing, like expanding inwards. How do I make it expand on the outside?
Yeah, it's mostly about actually two things. This scaling down the spiral looks nice, and but sometimes it's when it's actually that's not the main thing. Main thing is like when it's the whole big module of this like eye looking module is kind of copied and then rotating and then coming back and colliding, right? So there's a moment of branching, which is like right bottom side of the first agent, like first big eye module, and then like I say it's actually, but the one of branching like a higher level branching is having specific angle, and then that ends up like a repetition of like a big eye and the big eye and then big eye. This rotation, like the first rotation from one big module to second module, that's specified by at the moment of branching. Can you?
Yeah, I'll show this now.
Yeah. So that's dictated by one angle somewhere in the code. So
yes. So
I kind of need to see the result to identify that. Although, yeah, can you also show the result of the image?
Is it possible to share both at the same time?
You can show whole screen if you can. That would also show the back desktop as well, but
in my option here, they're only showing like one screen. How do I share the whole screen?
Right, is that like option called screen? Screen means the whole desktop, and the individual window is only one of them.
Okay. Yes.
So yeah,
Okay,
screen
yes.
is a thing to choose.
All right. Yes. So
Yeah.
it's here, and then
Yeah, exactly. So
it's
that
here,
one.
and then I can play.
Yeah, that one. So yeah. Yeah, so can you zoom out a little bit? So what we want to see is that like a bottom, you see the bottom of the first big eye, there's a start point of the second eye, right? Actually, not
Yeah.
that one, the whole thing, I think, and then, right. So you have like a curling pentagon thing, like a first 1, 2, 3, 4, and fifth one, actually the second, so 4 of this pentagon is a kind of group, right? That's a group of things. The second group has the smaller 4 pentagon, but the bottom of the first pentagon, it branches to the next eye, right? So that's the location we want to see. And then, so in that case, what is that? Yeah, it's like for something is, some clock is 1, and then some clock is also 1, and something is end. So clock 0 and okay, the first next line, like the upper part of the code, like clock 0, 7, then clock 1, 0, and clock 2, 3, and then next rotation minus pi divided by 2. The thing. Can you change that number to be like, what would be the good number? Not 90 degrees, so like divide by 4 instead of 2. The shallower divide. Okay, first of all, I'm not 100% sure that is the location to change, but actually, no, that was not the location to change. So I say it's different. So put it back 2, and something to, so in that case, okay, clock 707, and then maybe clock 3, 4. One of those, like inside the clock 4 equals 3, you have 3 angle, right? One of them should be that thing we want to change. And then I'm not sure. That's maybe the middle part, like the inside the clock 4 equals 3, and then there is a rotation pi divided by 3, and then pi divided by 2, and then pi divided by 3. Can you change the pi divided by 2 to 3 as well? Again, so I'm not just guessing and without not thinking too much. That didn't change. So okay, so in that case, change the other. Or change other, like a top one to be divided by like 6. But actually, yeah. So this isn't like a very logical thing to do, but yeah, keep going, and then that's totally kind of quick way to do. Also, no.
But I think number maybe, I don't know.
Actually, yeah, if we, yeah, like definitely that's the end of edge, which is 0 equals 7, and then the edge, second edge will be something equal 1, or clock, where something equal 1 is, where is that? 0, 1. Nothing equal. Oh, actually no, there is something equal 2. So yeah, definitely one of them. So we changed like a middle inside the clock 4 equals 3. We changed top 2 and it didn't work. How about the bottom one? The other one, the rotation minus pi divided by 3. Can you change that angle to be something else, like I don't know, but divided by 6? Not really. Okay. Then where would that be? One below, like else if something. Yeah, that one. Can you change that to small number? Yeah. Is that slightly change? Is that slightly change? What if you put 0 there instead of divide by 6? Like make a whole thing, or not divide by 0, but delete pi and put 0, meaning no rotation. But yeah. So it's slightly changed, right? I mean, not directly colliding. So that's one thing. And then, but it would still come back at some point. But if you keep playing with this number, like it was rotating like minus pi something, you could do that with a positive number or opposite number rotation, and that's one thing. Another thing would be like but yeah, that it getting more interesting. But another thing would be if everything is keep getting smaller and smaller, at some point the collision detection is actually happening with the absolute size. Like if it's too close to like a distance 1 or 0.1 or something, then if the agent itself become size of 0.1, that gonna collide, and then because next one is too small to something. So if you maintain the whole thing is you can scale up some point. Like if you scale down, and sometimes if you scale up again, and in that case you can maintain the kind of something becoming small, but once you become big again, and then becoming small, so you can insert some kind of multiplying like a 1.5 or 1.2 once somewhere. Then in that case it doesn't keep shrinking, and it might become something. So that's the thing. Changing the angle not to collide itself, and then scaling at some point. That's the thing. So to kind of make it look interesting. So that's all.
Thank you.
Yeah, I think. But right now, yours repetition is a kind of one sequence, right? Like a repetition of a big eye and the big eye and the big eye. So if you have one more branch somewhere, not the same location, but somewhere, actually you have in the code you have 3 branching code, but I think 2 of them is colliding at the moment. It tried to branch, so it didn't grow. So if you play with like a clock number, I think the top 2, which we change the angle, but nothing changes. I think that those are the one which was trying to branch, but didn't happen because it was colliding something else existing. So if you play with like number of the clock 2 equals 0, maybe change to 1 or 2, or clock 1 equals 2, change it 2 or 3, it might avoid the collision, and it might grow. In that case, you have 2 things going, and it keep growing. So, or you can find another location to branch out. But yeah, so making more branches might create or might cover whole area. That's different type of kind of distribution. So yeah, that's one possibility. But interesting shape. So yeah, looks good. Right. Thank you very much. Okay. All right. So we can go back to the tutorial. So okay, that's what I was bringing is. But anyway, then what do I do? So I was running this one. So okay, let me stop this one. Let me stop this one. Whether you to stop processing, you can also, I mean, you can click this stop button, or there's also a shortcut to stop the process by Control Q. However, I need to share my screen. Let me do that. Okay, so all right, then to continue the tutorial of this clock stack algorithm. So one thing I want to actually, so first of all, there is a many variation or example in the tutorial, so you can check them, play with it, and then you can see what's happening. Like, so some of them are like something we are playing right now, like changing the angle to make the orthogonal glitch to circular or triangular, and then there's also example of like a random number. So that introducing random number to the bottom level, like a clock 0 is like this example. And actually there's several different level of randomness happening, but so maintaining the bottom level straight, but one level up is a random in this example. Also, this also shows the random number use in the clock comparison. So again, putting random number inside the clock level will be devastating. So that's would be something to avoid, I guess. If it works, it would be great. But so there's a way to use randomness, not making it horribly going wrong. So this is like random number comparison with the clock 2. So this is like, the thing is that, so this random number, this one is slightly different with what I showed a moment ago, the random number using the method called get. That was giving you a floating point number, but there's another method called get int that generates integer, so which is more kind of appropriate for the use of clock number comparison. Then now, so this random number generates, or integer random number method generates some number from 3 to 10. So it would be like 7 or 6. But however, this doesn't mean sometimes this like this condition become clock 2 bigger than 6. Actually, every single time clock is checked, this number changes. So it's when it checks this condition, sometimes 5, sometimes 3, sometimes 10, sometimes 6. I mean, so kind of it keeps changing. So it's a bit difficult to keep track of. Well, imagine what will happen. But however, if you use the equal, and the clock 2 is keep increasing increment like 0 and 1 and 2 and 3 and 4 and 5. If you use equal, then if random number sometime become 4, and then the clock is now 3, so it doesn't match. But next time it's 4, but now random number changes again. Once it checked, next time random number going to be different. Well, could be same, but most likely different. So become like 3. So now it kind of pass the moment it's supposed to match, and then kind of, so meaning this condition never happened. But if you use this comparison with like a greater than, then in that case, at some point it's gonna match. If clock 2, even it kind of pass the moment of equal 6, if it's bigger than 6, and if it's now 9, previously the random number generating like a 10, and it misses almost kind of close, but next time even it miss, it matches, and so meaning you can make sure this condition gonna happen. So actually, when you use random number in the comparison to the clock, it's safer to use the greater than. But anyway, so this example is just example of use of random number in this condition. So, but anyway, so that's a kind of one technique to do when you want to randomize the moment of like the condition. But anyway, so I'm just giving you like skimming through the example and just picking on the point, and I just want to explain some of them today, and some important part for our kind of project. But actually this part is a bit important, so I might revisit here again. But So that's a randomness use example, and then this is another randomness example use actually again here, and this one is just using the random angle, which is a bit easier to use. So yeah, same thing happening here, like a use of random number here. Actually, let me show one example of randomness use in the clock number comparison. To show the example, I want to have a simpler one. First of all, I save this code, which I was playing with before. Okay. This, I'm not sure this was saved one. Okay, then I want to start with a simpler, maybe this code, this like a square sequence of square, and then okay, that I could not delete some of the stuff. So when I have this code, and then when I want to randomize some like number of clock, for example, if I want to randomize like length of edge, how do I do? So the technique is same. So use random integer, but with not equal comparison, but like a greater than something. So this number is specified by this number. This 9 is a number of agent on one edge. So if I use first rand and dot int, so that's an integer random number, then you give range of number, maybe 3 to 15, and then so if I put equal, they're gonna miss sometime. Actually, most likely gonna miss. They never match with this condition. So what's gonna happen is like they don't turn. Is what gonna happen. So yeah. So right now they keep missing. They keep missing the moment of the current number matches, and then this matches. And actually, what actually happens is like this number keep going like 10, 20, 30, 40, 50. And then now that never matches with this one. So using equal with random number is have the preferable result in this way. So that's why we need to use this comparison of greater than and then or equal. So I mean, either is fine, just greater or greater or equal to, and then so in this way you're gonna match or you're gonna capture even if you miss some point. So then now each edge is kind of different number. I mean, most likely. So that's how you use or you randomize like a length of agent or like a number of sequencing agent. You can randomize that with this I get integer and greater than. So that's a kind of one technique. Then so that was good things to show. Then sometimes make kind of spiral if number matches. Then let me stop this. Then save. So that was one technique, and then next, this one is just changing the rotation to 60 degree or 30 degree, and this is kind of base angle, like a straight line, not straight now, and this is like 5 divided by 180. I'm not sure why it's multiplied 1. I think I was playing with some number. Then the same thing here. So then this is this random number group comparison example in a higher level of hierarchy. And then those are more randomized angle and also group comparison. So then other things. So other things, this is just a variation, like a geometric variation. The example I showed so far was kind of based on square 90-degree grid, and then but it was just an example, not necessarily. That's not essential to this modular system. So it can start with any rotation, any kind of repetition of things. And in this case, based on like a triangular shape module, not really module, but like sometimes as a natural result, it creates a circle. So circle is actually a byproduct of the behavior, and then so I gonna just show how it grows, and then so it's almost looking like a rotating, but anyway, again, so base logic is this triangle and branch. So like, so bottom level is straight, but only up to clock 0, 1, meaning clock 0 is start from 0, and 1 meaning the 2 lines. So 2 lines is just one edge, and then always turn negative 30-degree or positive 120-degree, and then actually each of them have different kind of clock to turn. So yeah, something has happened, and then but so the triangle, kind of sharp angle triangle, is created by 120-degree. Yeah, 120-degree, and then negative 30 degrees is a kind of more gradual turn, which sometimes create a circle, like a circle of triangle. However, most of the time they kind of correct each other, so not necessarily going that way. And then even when actually I don't know, just another technique, or like a small kind of coding technique to control the agent is that, I mean, we are using randomness in angle or the clock comparison, but there's also another kind of easier way to kind of adjust like branching. So exactly the same way with the technique yesterday, like introduced a probability to branch. So you can actually still do that here. This is essentially whole branching system, right? This is like hierarchical branching system. So, but still the irregular branching technique applies here. So if you put like 1%, 20% or something, then in that case, it decreases the probability to have that happen. So now the circular part is actually kind of dominated by this 30-degree turn is dominant, and then actually that 120 turn rarely happens, and so 20 to low probability. But so now it kind of start becoming the closer to the original condition, but slightly different, more circle happened, and that. So this, but what I want you to understand this relationship, like there's two rules there, and one of them is kind of dominant and other less dominant, but you can have a balance where you introduce either by randomness, but there's also other way to do that, like by clock timing. You can also do. But anyway, so but you see this kind of a little bit of random but kind of spherical distribution is introduced by this random probability. But when you did not have the randomness and they all kind of rigid, strict logic, the whole thing is, I mean, rigorously repeated, but still you get the same sense. So there's a continuous like similarity to the other, and it's related, of course, that they are same logic and just switching the logic in slightly different way. So Other thing would be like a rigid control. So one way to control like branching is like the randomness, like yes, the technique we saw yesterday. Another would be the control by the clock. So you could control by the clock, and then so I a little bit I kind of limit the moment to have this branching happen only when clock is certain number. So which is maybe clock number 2 is kind of changing. So maybe I'm going to use the clock number 2. Clock number 2 equal. Actually, no. One thing is the this one is control clock number 1, and the clock number 2 is higher. Usually, higher clock should control the lower clock in a way. So I'm gonna do this. If I'm gonna limit the 30-degree part, and the clock number 1 equal maybe 3. So this now 30-degree turn, actually, so that's a big problem. So I need to have this. This is triangle, so it cannot. It's gonna stop at number 2. So 1, 2, 3, and stop. So it needs to be at 1 or somewhere. And actually, I'm limiting too much. So what if 0? Or actually, by the way, there is a condition you can use like some symbol similar to this. This is a connection to put two conditions together as and, like this condition applies and also this condition applies. There is another type of combination condition which is this condition applies or this condition applies, which is this two vertical line or bar symbol. And then so I'm gonna say if I can let this happen when condition like clock 1 being 0 or clock 1 being 2, and then so okay, it's not that different. Actually that's all. But anyway, so I mean this one was not a good place to play with this logic, but so clock clock control or randomness control is something you can like adjust the branching, mostly the limiting. Like if you have too much branching, and you can limit some of them, and then yeah, so that's one thing you could do. And I'm still wondering if there's a way to limit.
Sorry, could you repeat this again? This 2 line, what do they mean for the code? Like I didn't understand.
This line or
the 2 bar lines?
How this one? Yeah, correct? This one is a code symbol called or, and then so okay. Let me write compare two different ones. So previously I was talking about this this symbol, which is called and then so when you put two conditions together, then actually last time that was using like a 2 different clock, and then actually other example had that like what. So this thing like clock 2 being 2 and clock 1 being 2 and clock 2 being 0 and clock 3 being 3. So this one is like you have to satisfy all 3 conditions to run this code. So that's the and.
All right, I got it. That's or. Right. It represents or. Yes, so I understood.
Yeah.
Thank you.
That's what that is. Yeah. Good. So then okay. Then let's move on. So anyway, so that's a kind of branching control technique. Then so actually I want flip normal thing happening. So I want to talk a bit more about the kind of transformation operation in this system, and then flip normal. Okay, I'm gonna talk about flip normal, but it would be good. This is not necessary. Okay, I'm gonna have simpler example. I'm gonna write down simpler example. So before that, I'm gonna save this. one. Then I'm gonna start with simple one like this triangle. So there's one triangle, and then I want to have branch, but I want so flip normal is mostly about like changing the rotation angle. So go one, go one. I'm making like a branch at one moment to the other angle. Or actually, I can go straight. Then in that case, I don't need this. But actually, no, I need to make it two. So first, I'm making just a several triangle, like one triangle happen here, and another triangle happen here, and another triangle happen here, although it's colliding itself. But one thing I want to introduce is the transformation operation called flip normal, NML is as a abbreviation. So this makes the whole inside the system flipped, and then rotation going the other way. So now you see that, I mean, kind of zigzag, but basically trying to make triangle in the alternate way. So actually, to make it slower, I'm gonna make the length of triangle or edge of triangle longer. Then, so you see, yeah, actually this is easier to understand. So this kind of switching thing is by the flipping normal. So again, as I mentioned before, each agent has coordinate system or XYZ, like local XYZ inside. So that's flipped. Like up now become kind of downwards in a way. So yeah, so in that world, the rotation of the positive rotation is like this rotation meant the other way in the global world. So that's how it's happening. Then, but there's the exact same effect can happen when you rotate whole geometry, or actually no coordinate system 180 degree. So now actually I'm gonna talk about this three-dimensional rotation. So let me do that. However, there is some example of that somewhere, although not specifically talking about the transformation. So I'm gonna just write down being away from this example. But so first, let me save this example. So flip normal is one thing which kind of start talking about this coordinate system control. But so far we are playing with rotation, but it was rotation on the XY plane of local coordinate system. So if the whole local coordinate system is tilted, rotating on that coordinate system. But you can also change the direction of coordinate system. Actually, when you rotate object like a 90 degree, whole coordinate system is actually rotated. So basically, you can always imagine the agent is like a box, and then the whole box is always kind of rotating and changing and moving. So that's how you can imagine. So, but you have, so flipping is like a one thing to go upside down, actually left and right kind of change. But you can rotate in three-dimensional way, not only like XY rotation, you can also go up and down, and you can also, actually, you can also go like this way, like a rotation around the axis, like a direction going forward, like the front axis rotation. So that's something you can do. So I'm gonna talk about that. Which is, so there's a method, there's a three rotation method called pitch and yaw and roll. Actually, first of all, let me show example. So I'm going to talk about maybe this rotation first, like going up and down. So if I rotation of not xy, but like along the side axis, like going up or down, is called pitch, and then that's the rotation to go up and down in 3 dimensions. So that let me just show what I mean. And this is still taking the radian, so like pi divided by 4. Actually, it doesn't really matter, but slight rotation. So this one, okay, first of all, this is already this is tilted and going back. So what I need is something else. This gonna make it go right into itself. So let me rotate that as well. So I can combine with the rotation like with this pitch rotation with other operation. So you can put like all the transformation operation together in this line, and like the way we combine like rotation and multiplication. So you can keep putting many things together. Then so actually, because this is triangle is colliding back, so I'm gonna rotate a bit the other way first, and then use the pitch to go up. So okay, so did not expect this, but anyway, so but at least you can see here, like first triangle here, and the second one I rotated 60 degrees the right side, and then also pitch is going up a little bit. So it went up, although the whole thing is right now rotating, and this pitch kind of make it this we are sliding as a plus, making pitch going upwards, but it's kind of going like the like a 60 degree or whatever, like a triangular, like hexagonal direction, and then ended up somehow going down. So like for this triangle, still going up, but when it rotates back, it goes down, and then yeah, so that's what happened. So but anyway, so now actually, so the direction we are going is a 3-dimensional. So now I'm introducing 3-dimensional operation to go forward with more complex geometry and stuff. So then, but anyway, so pitch is one thing, and then actually I want to show simpler operation. So I'm gonna save this, and actually I go back to square to show easier example to understand. So first of all, I don't want triangle, so I rotate 90 degree, and then I say this should change, but by the way, the shortcut for processing to just run is a Control R or Command R. You can just type it, and then they should start here. Okay, right now not necessarily easier. So let me first make a simple sequence of square. Actually, square operation, although it's going back, so I don't like that one. I want this to go straight as a sequence. So now, so we got the original sequence of square. So, but I want to introduce the pitch rotation. So this is a moment of branching when it goes straight, and then, but I want to move it upwards. And so I put pitch here. And first I want to put small, actually, yeah, small amount, just to see the effect of that. In this case, I should really see that in perspective. So you see that now it's kind of rotating, but in 3-dimensional way in the kind of Z direction. although this is regular angle, so it just come back and then stop there. So, but now you see the operation is happening in this like xz plane, but still this kind of square is a module looking thing. So now, yeah, we are really dealing with three-dimensional accumulation module in many different way. So then, for example, actually, as an example, okay, so in that case, I save this. As a example, I could turn this 90-degree, and then that would go back quickly, although it creates a cubic shape. Although, I mean, some of them kind of collide in at some point, so it collide. If you really want this edge, you need to think about either not to collide or branch some other location. But anyway, so first we didn't see how it came back, so I start with a perspective view. So when you want to start with perspective view, you can type this command called pass. Yeah, so it's actually, but actually the for view we have in the IGO kind of a simulation window is a top view and perspective view, and then side view, and then front view. Actually, there's a back view too. So those are the thing you could do to choose. Although the elevation is something you don't really usually use, so either pass or top. And there is actually another one. If you want to have, if you don't want perspective angle, you can also put the axon, and in that case, it just doesn't have the perspective deformation. So yeah, that's something you can use. But anyway, I go back to pass to see what's happening in 3 dimension as a movement. So yeah, now I think it went. Actually, I forgot which is a kind of main rotation angle, but so it's three or four came in the back and then collide. So I think what happened is this one is a final square to draw, but it's supposed to go like around. However, it collide in the first edge and the first edge, and they didn't turn and come back. So I think that's why we don't have this edge. But however, so now it's in 3D. So now we can think about three-dimensional branching. So we have like a branching in the XY direction, and we have branching in the XZ direction. Actually, it doesn't need to be XZ, any three-dimensional direction. So for example, we go back to the rule. So now we are rotating like upwards and then coming back. What if we branch straight, or when should I branch? Clock 1 is 0, and okay, super easy thing to do is keep going. Like if I don't put any transformation, that means it keeps straight, so it would make the straight this thing. Actually, another thing is that I did this always. Well, actually, not always, but I didn't check the clock 2. I only checked the clock 1. As a result, it goes straight on the x direction, but also goes straight in z direction and on the negative x direction, and the so. But you see that like a continuation logic, right? So we saw this kind of view in XY before when I was playing with this one of the example, like this example. Well, actually not really, but some examples similar. So, but now it's happening in XZ direction, but on XY plane still doing sequence of square, but in Z direction, or X and Z direction, this grid system happening. So okay, so now we have another dimension to deal with, and then, but yeah, that's some kind of main thing to talk about now. So yeah, so now it's got a bit more complex to think about three-dimensional branching, and then well, also potential. You have more potential things to play with, and then so pitch was one thing, and then one thing I want, but yeah, play with is controlling or limiting this to branch. But that's something I talked before, like putting randomness or putting a clock control gonna limit the like a moment to branch, and then they're gonna create some certain aggregation. So, but anyway, so pitch transformation is one thing. So, but I mentioned that there's a three-dimensional rotation, and then that if you are familiar with the computer graphics, you would know this kind of rotation pitch your roll, and you might have seen this image or something similar. So yeah, it's actually airplane kind of control based angle system. So pitch is like up and down, and then yaw is like actually XY plane rotation, which is actually what we are doing. That the rotation, well, when we are using the command just called ROT, the rotation, that was the yaw rotation. Well, that was the basic rotation on XY plane, local XY plane. Then the third one is a roll. Rolling is like around the front axis. So that's how it does. So for example, okay, let me show that example. First, I forgot if I save us, so let me do the first, and then I don't need this branching. So if I change to this yaw, so I was using pitch to go up, and then now I can rotate this way. Actually, just to illustrate what I mean, I make a smaller angle rotation. So now, actually, no, yaw is XY plane, so I don't think that. So I wanted to show rolling transformation. So you see that, I mean, that's rolling. So literally, so it's kind of rotating along the local front axis. So it's kind of going that way. And then, yeah. I mean, if it's small amount, it creates this kind of wavy thing. But if it's a more distinct angle, like a 90-degree rolling rotation, then that's I mean, that thing. So I mean, still also not, but I mean, you see the logic clearly. And then even like as I mentioned before, like flip normal gonna change the rotation angle, like clockwise, anti-clockwise. Same thing happen when you rotate roll in 180 degree. The different thing with the flip normal gonna be that there's a one issue, but like right hand coordinate system and left hand coordinate system, that kind of thing is that different. But mostly right now it doesn't kind of matter. But so that's another rotation system you can use, and then you could even combine with pitch, which I don't know what's gonna happen if I rotate this way and then that rotate that way. So it's gonna be like a really not really twist, but like three-dimensionally tricky thing gonna happen. Also, I mean, yeah, this one is a stepping function. So what happens is so pitch and then rotate made a kind of flipped, and then so in the next step, this second corner of the step originally supposed to come back because it's 90-degree kind of internal kind of inward rotation work and keep going upwards, but because it's rotated 180, so now coordinate system is faced on the other side, so their upward is the forward, so that's why it made that zigzag thing. And yeah, so that's what happened. And then yeah, that's one example, and let me save. So then another thing I want to show next is that so right now I rolled 180 degree. Rolling 90 degrees still maintains the orthogonal world. However, it kind of complicates the behavior in hopefully this way. So I mean, still kind of zigzag about the kind of diagonal. And then yeah, that's one thing. And then what happens if I put the branching? That's another thing. Kind of not in pyramid, but like growing one corner to the other, right? So which actually I didn't know what this is what happens, but but again, so three-dimensional modular repetition in modular way. So hierarchical way. So that's another thing, or another kind of layer to think about. Plus, yeah, it's interesting thing, plus difficult thing to think about. However, this part is gonna be getting more realistic or useful for modular structure design, especially in the space. Like you don't need to stay like a ground. There's a whole three-dimensional space you can use to explore a possibility. So going 3D and then three-dimensional transformation is very good to explore that direction. So that's a three rotation, and then again the yaw is exact same with rotation. So yeah, you don't need to think too much. And then out of curiosity, what's gonna happen? I use yaw here. It is colliding to itself or grow in some other location. I think colliding itself. Anyway, so that's a 3D rotation, and then okay, this is something. So comment out and save us. This unsave. So okay, that was one topic, what like a technique you can play with, and then another thing would be actually, but that was a kind of main thing about transformation. And then we have like 30 minutes left, and so but the things okay today, what I want you to play with for assignment is developing this modular propagation system. I not system, but just line work. Or actually, I want you to play with 3D. So using pitch or roll, then start thinking about like our space architecture project. So, well, actually, doesn't need to be. So some of the 2D alignment or like aggregation is very interesting, and then you can start from that, like just adjusting or changing something to go 3D. Plus, if you go too crazy in terms of like weird angle to rotate, etc., that start become to translate to modular construction system, like a hypothetical project. And however, it's kind of there's a trade-off. If you limit yourself, not much kind of interesting happen. But if you unleash your kind of potential the full amount, maybe difficult to come back. But what we want is some everything. So maybe today you can just go any kind of crazy direction. Then maybe later we're gonna come back to think about more not realistic, but like feasible. I mean, future feasible hypothetical scenario. So then okay. So let's see. So for that, I'm gonna maybe introduce several more techniques for you to play with, or something you can play with it. And then I mean, color thing. There's a you can play with color, although that might not necessarily too useful for the modular approach. Although you don't, I mean, unless you color your module in a different grading color. But yeah, most of the stuff is really like a play with the yaw and pitch and roll for 3D. So to mimic this some kind of molecular layout of atoms, like it's kind of usually like some molecule, actually not really one molecule atom, like a combination molecule, like a sequence of DNA or those kind of protein. They have very specific angle to lock into each other, and then so that has some angle in 3D, and they kind of keep twisting, and then so that's that could be simulated by this combination of 3-dimensional rotation. And then something like this might be more like architectural thing. So this is something else. So maybe more I'm gonna pick some of the example and explain it, and then today I maybe that I'm gonna wrap up there, and I'm gonna ask you to work on this 3-dimensional line work, 3-dimensional modular line work for the assignment tomorrow. Then first I'm gonna pick this. So actually yeah. So this one, you can see the code, and yeah, that's a 3-dimensional rotation, a lot of happening, and then actually I still keeping the point, so maybe I can hide the point here. And so this code is making this triangular kind of column and bending. So kind of triangular pipe moving, kind of spiral, triangular spiral, and they keep moving and then branching. So
I have just one question actually. How can we hide elements in processing? I mean, like keeping the elements, like in that case, for instance, that you comment out the points. So now the points that they're not in the model anymore. But if we want to keep them but not seeing them.
Oh, you want to keep them, meaning you don't want to see, but you
visualize
want to see. Okay.
Yeah.
But you are assuming like you're gonna save in like a file, and then you want to get the information, or okay, first of all, for that there is a hide command, like something you can add like in this way. In this case, it doesn't show up, but it exists. And then okay, first of all, I didn't explain about the file saving. Let me do that first. So right now, so right now this point is there, but it's hidden, and then but it stays hidden in processing. But when you save it, so saving is something I haven't talked about. Saving is something you can do after you run simulation, and then so in agent simulation, saving is about a snapshot of this moment in 3D. And then what you do is I have the shortcut for saving, like a Control S, and in Mac Command S, I think. And then one tricky thing is this is some problem I'm having in Process 3, and the saving window shows up behind or somewhere behind, so you kind of need to search where it goes. Then this save window shows up, and then you can just save. But one thing is that you have to save the code beforehand, because this goes to the location where this processing code is saved. So if it's not saved, it kind of stays in the, like a system's temporary location, which is kind of usually hidden. So so the save some line file. So default is line file, and then actually it used to be default 4, but now 5, and you can also save OBJ. AI is 2D. PNG is something else. That's texture wiki. I don't have now. So by anyway, so line file, if you just save it, this is saved in the location of this processing file saved location. So which is exactly. Actually, no, it's inside processing. Yeah, this one. So the code is code number 20. So it actually when it's saved, it creates the folder called data, and then this line the saved on. So if I open in the right now, in the past I had the problem opening file in Linux version 6, but now it's solved, so it should work. But anyway, so is that coming? So where is why? I don't see it. Okay, first I can stop this. By the way, I pause the agent, then save, but you don't need to. You can just keep running and then save, and then the moment it's saved, that stops. But or something. Okay. Then I'm gonna stop this, and then right now is coming somewhere, and okay. I might open Rhino twice. Okay, so it's here. So so this was about saving. About the hidden point, the points are staying as actually wait. Okay, I thought hidden point stays hidden, but it doesn't. So okay, in that case, it doesn't answer your question. Or so okay, in that case, it's not hidden point, not saved. One thing you okay. Depends on what you want to do with hidden point, but if you want to have another thing you could do is you can make the color 100% transparent, which would be a bit weird. It might affect the appearance. Doesn't. Well, actually, slightly. But in that case, if I save this file again, actually, usually Rhino locks the file, so I have to save a different name. But that's another thing. To that 100% transparent point will show up opaque point in Rhino, so that's another thing you could do. And then kind of apology that I didn't save the hidden point as hidden object, but yeah, that's one thing you can do. Does it answer your question? What is that what you intend to do?
Yes, thank you.
Okay, good. Right. But if you actually just play with, or actually if you just need that information at some point to do in the modeling, you can just run simulation twice, like one with the without point and one with point, and then use that. Well, actually, you save as for geometry purpose, and you don't create points for animation purpose. So I mean, tomorrow I'm gonna show you how to like screen capture every frame to produce animation. So that's one technique, and then you might have another code for that with same simulation. So that's actually what I usually do. So, but anyway, okay, so it's good that we covered saving. So then maybe another thing I can actually, so I was just talking about this example. So going back to that agent simulation, actually, so this one I'm just explaining like what's happening in terms of like a rule and then transformation wise. So it's triangular spiral, and then bending. So actually you see there's some effect of transparent point. But anyway, so actually so not perfect. So I want to see the simplest form of this, which is, I think, this part. So to do that, I want to just hide whole thing. So one triangular spiral is made out of this command, or like yaw is a regular rotation. So like a 1/3 of by the 120-degree turn, and then actually that is not because this. So this is greater one. So actually that's circular move. So 120-degree and then pitch kind of make the triangle goes kind of spiral. Although actually pitch one doesn't bend enough to avoid collision. Actually, no, that's not what's happening. So what's happening is that each even the straight line inside the edge, like one edge in the triangle, it's not actually straight; it's slightly kind of going up in this case. So doesn't need to go that way. But one thing I want to show is if I can make a straight spiral. So if I don't have some rotation, it might not bend in like a circular way to go back. Actually, no, that's a bit tricky. So it's actually that was too close to stay and then kind of quiet. So, but actually, so the combination of these two systems, like every time 120-degree and then slightly pitch going up, and then every 3 roll change, and then also 120-degree and then pitch. Actually, so this yaw and pitch transform is the same, but this is different. So it is extra roll rotation. So triangle slightly, I mean, shifted triangle already, but the next one is actually whole thing is a bit shifted, not too quite mostly. Then as a result of avoiding collision, they rotate. So it doesn't even come to same location. So, but for example, if you are interested in like the previously what I was interested in this example code was branching out some point because I knew this wanna collide itself and stop, and that's why I wanted a distribution like outside. But if you are interested in maybe spiral, so in that case, what you would want to do is you want to avoid the collision here. Then to change the angle of like a spiral, kind of bigger spiral coming, this kind of pitch of spiral, not pitch of the rotation angle, but like a screw pitch type of thing. So if you want to go wider, maybe this triangular move gonna be slightly having different angle to move slightly that way. So maybe I should not rotate exactly 120-degree, and then maybe slightly more. So maybe I can add some number here to if it changes the kind of rotation to shift more somewhere. So this part is just a kind of eyeballing thing or just guessing game. Plus this is too much. Could be interesting, but I changed that too much. So although if that's something you like, you can keep it. And in my case, I wanted to have kind of tighter spiral rotation. And then yeah, now it can happen. So that now it's spiraling this way, and then maybe now I can add branching to it. So, but anyway, so I'm just showing like when you see something and try to understand, then you see and having understanding of that, and but also have the imagination what you would want, and then kind of reverse engineer to the number. In this case, I wanted to adjust this spiral kind of distance, and which was caused by this. Actually, it's also caused by this, but then now you have the control, and then you can start from here. Then those by more and more. So if then, for example, if I bring back some branching stuff, okay, maybe I can just have one, but so I'm not sure that's the preferred location to make branch, but yeah, something happened. And then I did not think about like angle relationship, so it's kind of going whatever direction. I mean, it's regular repetitive angle in 3D, but it's just a result of branching at the clock 100. So I only check that. And then another thing about this is this system or this example doesn't have much hierarchy, meaning this does not use the like clock number 2 or level 2 or 3. So which might be lacking some organization. So now you kind of start to see there's a kind of almost Christmas tree like organization, but yeah, anyway, so kind of this is one kind of design process example. And actually one more thing I would talk would be the color, which you can play with in the assignment work, although which might mean something in the modular design later or might not, I don't know. If you have good use of the color, then great, then you can use it. But for today, I'm gonna show you that you could use exact same logic with yesterday, like using color by the ig.time, the global time. You can still do that, but you can use the clock for the same purpose. And then you could put just the time number, so the clock number. So this one is a clock 0. I think this one, because this one doesn't have much hierarchy. Clock 0 is always like 0 to 100. So if you multiply 0.01, this number always changing the 0 to 1. So which actually corresponds to the one sequence from the beginning to the branching point. So that's actually, so that segment from this bluish edge to another bluish edge of the branching is 100 agent. So the color corresponds to that. So meaning color has some suggestion about the modular system or modular kind of sequence organization. But anyway, so that's one option. Like you can use a clock for coloring, and then just for like colorization of the modular system. And so that's one example. Then let me pick another example somewhere. And the tutorial. Another thing is maybe like, so this is full of like 3-dimensional transformation, although also not. So let me copy and paste this one. So this one has a several level, like a 0, 1, 2, 3, and 4, so 5 level of clock used. But what's happening in this code is so making cube. So something like something similar to the previous example of using pitch and roll. So actually, this also uses a pitch and roll in 90 degree. So everything is 90 degree, but yeah, the kind of diagonal aggregation, although a little bit trickier than just diagonal. So it's kind of going up and down because of some of the switching of by clock, higher level of clock. So, but one thing is that this because this is line agent, so it's just line, and then we are assuming that each line is going to be replaced by module later for your project. And then, but when you are kind of closing square, if you want to make face, you need to fill that face with material if you are making like wall or antenna or some membrane or something. So even when you are imagining some kind of modular construction in space, like antenna usually usually in the traditional engineering approach is that you for the fabric or some collapsible material and then put it there and then enlarge. But another alternative approach which might be costly, but is that you assemble each panel and then it goes there and then kind of put together and then make a face. That's as idea feasible, not necessary for cost efficiency. But some of them are like the in the lecture yesterday I showed the example of research in space engineering that the antenna is a combination of modular robots. However, each module has an unfolding module, so it's combination of multiple unfolding process. But each of them is kind of modular component built by robot. Actually, well, the robot are delivering the module to the location. But anyway, thing you could think about is like I'm start talking about like some ideas about your design project that when we think about the hierarchical composition and aggregation, you can either go bigger. If you are imagining something like a space shuttle carrying the component for International Space Station, you are imagining one room size cabin cylinder. That's a module. And then you could think about what you can do with this when you have multiple things to, and if you put hundreds of them together, maybe they could start having different kind of function, variation, some other meaning to it. That's one way to think. But another way to think is, what if your module is a micro module? You don't start with this kind of inhabitable kind of and tight space. What if one module is like a 10 centimeter block, and then this gonna make the either habitable space or some meaningful device for space exploration, or antenna or some other or solar panel or those. So in that case, you might want to like make a skeleton structure in one way, and you also want to fill the face with membrane or some panel. And they are different type of module, but meaning they're gonna have different behavior to get the assembled in the location or grow. Also, so I'm just suggesting like so this agent in the screen is showing the one way to fill the face, although it's still line and it's actually scaling down, which is something we tricky things to think about the scaling like 0.9 every time. It's gonna make very many different size of module, which might be fine, but it's kind of repeated in many locations. So, but yeah, so in this case, making agents, line agent making cubic space inside as a result of like not only growing on the edge, but also going into face to fill the face. So that's a kind of one thing you can think about when you imagine your modular assembly project. So, but so that was just kind of an idea about that. But the actual thing happening is like actually, which is not that too different from the example I showed in the pitch and roll, but so that's the location going like a diagonal cubic branching. So one branch is made and a kind of cube is coming back and making one cube. And then at the corner, it branches out to the another new cube. And then the other part is like this part, okay, sorry, this part. This part is the part going covering the face. So that spiral is created by this multiplication, which is not ideal for actual modular construction. In reality, modular construction, if you go in spiral way, you would like decrease the repetition number in each edge. Like if you go 10, next one might be 9 and 8 or something. Or you go one straight line and then all of them coming like at the same time. That's some other way to think about filling face. And you could also feel like a cylindrical way as well. But anyway, so yeah, that's those are the thing that's the logic it's shown here as example. So this is something you can play with in the assignment as well. Then in that sense, I'm gonna only because I just got idea. I wanna think about. For example, I mentioned like I'm start thinking about like a filling phase. So in that case, so this spiraling enclosure is one thing. When you put like a panels, it could fit if it's kind of carefully kind of layout in a specific way. But what if you okay, first of all, this is saved. I just want to show the other case of like all lines kind of coming straight up to fill the face. So first I'm gonna just make straight line, and then I'm thinking about like a cylindrical enclosure. So I want to go straight first and then branch out to the left and right at the same time. So I'm gonna make rotation 90-degree and then changing the clock. So what I'm trying to do is actually no, that's not. This happens every single time. So okay, then the other side. So this actually now going to I want to have like a both going both direction, but after going this way, I don't want any branch, like a first root kind of axis branching tons of line, but after it's branched away, I don't want any branches, meaning if clock 1 is like a incremented once, I don't want anything to happen. So I'm showing like a conditional kind of switch using clock. So first moment I want to have a branching, but the second moment I don't want them to branch. So like a second, like when higher clock is ticking by 1. So that's kind of what I mean with the kind of root skeleton or like the backbone thing. So I have backbone, and but after that I won't limit the of the branch. So no branching. So if I just have a straight line, it should go just straight unless they collide each other. Then, but what if I want to make enclosure? A kind of quick, easy thing I can do is rotating some pitch rotation, and but so that's what I meant with kind of modular way to enclose the space or make enclosure or some geometry. So in this case, one module is the point thing. So one module is going to be each. So I mean, I don't know what scale, and I don't know how you imagine that, like how you use this as a space structure. But you can make enclosure in this way or some way. So that's another way to think about it, like not thinking about like enclosed space combined together, or submodule kind of really creates the other thing. Although it's kind of difficult to imagine in space that you have to perfectly enclose the like inhabitable space to maintain the air. So that's a bit more engineering kind of challenges. Although as an architecture designer, you can imagine like they could do, and then like it could give more kind of possibility, like if substructure, like not modular space architecture construction, but the sub-module space architecture construction might give different type of function or a benefit, hopefully, and this approach. So that's one example of making surface or face of that. Then of course you can kind of need to think about how to close the end or what to do with some other location. But once you get there, now for example, you have choice to, for example, now you can have a branch in that hierarchy, right? I need to rotate. But anyway, so I'm just playing with this thing, but I think this needs to be negative. So, okay, so again, the assignment for tomorrow is going to be for you to play with this hierarchical line work system aggregation, but it's still, you can imagine like a just pure geometrical expression, or you can also start think about a space architecture looking thing or certain aggregation, kind of both. Actually, I want you to think maybe both way. Sometimes you can go totally crazy, like just playing with some example and changing number and this totally weird thing happen, and then that's great too. And or you can also start, I mean, can think about how you can use for your project. So both. So meaning maybe you can show me several versions of that, and then not necessarily like this is for the crazy expression and this is for space architecture, but something you are interested in. Actually, that's an important thing. Something please produce something you think that's interesting. That's amazing. So then they use any of the example here. Then of course through the exercise or assignment exercise, try to understand, because later you want to have more control on it. But this phase, like this is first time for you to think about or touch this kind of code. So first play with it and then see what happens and then explore that. Then through the process, hopefully you get some grasp of understanding how to control that later. So that's assignment. Is there any question about the assignment or anything we did today or something for coming days for the workshop?
I have a question.
Sure.
Is there, I haven't probably had time to look, but is there a part in the library for methods like, I mean, for creating surfaces from line, like loft or sweep?
Oh yeah, loft and sweep to exist.
This kind of thing.
Let me show you. There's a tutorial in some earlier, okay, maybe here. Yeah, in this section of the 3D vector and nervous geometry, yeah, there's a loft, exclude and sweep. So you can check this tutorial section. Yeah.
Okay, thanks.
Okay. So, is there any other question? Okay, so then, in that case, I'm gonna see you tomorrow at same time, and then same Zoom link, and plus I'm gonna send you this example code I wrote today later, and also please submit the assignment code you did yesterday, or the assignment you did today. So, all right, then thank you very much, and I wanna see you tomorrow. All right.
Thank you.
All right, thank you.